Yep, let's start.
Hello. Go, you start. You were the
Oh,
senior responsible person.
one of those things is true. All right, good morning, everybody. If you could begin drift towards taking your seats, we're going to go ahead and get started. So just a couple of logistical comments. We're going to have 4 back-to-back talks followed by Q&A for all 4 speakers. So hold your burning questions. For those of you who are speakers, when you see the 2-minute warning for the preceding speaker, that's a good time to go up to the techs so they can get your lapel microphones attached. Let's go ahead and introduce ourselves. I'm Diana Gentry. I'm at NASA Ames Research Center.
Hi, I'm Julia Maya. I'm at DLR.
Gail Cascioli, NASA Goddard Space Flight Center and University of Maryland.
And the last reminder, if you're judging Dwornik Awards, don't forget to, do it. Thanks. And since we're here and we have a few minutes, don't forget 12 o'clock today, the Venus Community Interest Meeting at the Creekside Park Room.
Right, 30 seconds.
Okay, so let's start. First talk will be given by Erica Kohler on the descent imaging of Venus via Da Vinci, Venus analogs with geologic implications.
Good morning. Unfortunately, Jim was unable to be here this week, but I'm happy to be here presenting on our project, also to be here such an early morning after the Hawaiian party with all of y'all. So thank you for showing up today. Today, I'm going to talk to you about a really special project for us. As many of you know, Da Vinci will be taking images as we descend below the clouds. We are in an in-situ mission, and I'm going to talk about a series of field campaigns that we did out in New Mexico to help establish what Vindy, our camera, will be able to discern once it arrives at Venus. So Da Vinci will carry a 1 megapixel camera to image the surface to evaluate topography as well as composition as we descend below the clouds. And yes, I'm trying to remember the bingo cards as we go, trying to help you out here. We're going to be doing this by taking a series of nested images and generating digital elevation models, or DEMs, using structure from motion computations, as well as band ratio imaging to be able to discern mafic from felsic rocks. I should have brought the bingo card with me. I apologize. Next year, maybe I'll do the whole, like, can I get a full bingo as I present? So what we are aiming to do with Vindy is to establish the ability to generate the scale between between Lander scales as well as subregional scales of the topography as imaged from orbit. And so in order to establish what we'd be able to discern from many of our images that we'll be taking, we decided to conduct a series of field work campaigns using drone images with our team members at New Mexico State University. So we went out into the field at about 3 locations and conducted drone simulated descents, as well as some different altitude passes that I'll go over with you all later, to generate essentially what we'd be able to see with Vindy. And so on this slide, what I'm showing is on the left-hand side, we kind of mapped out these sort of different altitude images that we conducted in flying directly up and down by using the drone. And we included a specific spin rate. And basically, this is generating the nested images with the structure from motion that we need to generate the digital elevation models. On the right-hand side are DEMs that we generated from these images. This is out at Doña Escoria Cone. And then we were able to take these DEMs and compare it with the ground truth images that the students out in the field took with their own cameras. Unfortunately, New Mexico is a great analog site for this campaign. Low lava shield volcanoes are very common on Venus, especially in like the 1 to 3 kilometer diameter scale. You can see thousands of them with using Magellan data, and New Mexico is a great analog site for these. Additionally, we're able to use hyperspectral measurements from the Goddard Hyperion instruments to that instrument measures in the visible range and the near IR range. And so we're able to take the broadband range that Vindy will be able to measure and overlay that with the DEMs that we generated out in the field to compare whether or not we would be able to discern felsic versus mafic rocks. And so that's what we overlaid here. And so by using AIDEN in particular, so this is a crater within a lava shield out in New Mexico. We were able to conduct a very intensive campaign. And so with this slide here on the left-hand side, we use Maxar data to generate a 1 meter scale DEM. And that will be similar to what we're going to be able to get with Vindy. And then compared it with a 4 centimeter scale from the drone images that we took. And this is basically what the Lander scale ground truth is. And we were using these DEMs to compare what sort of what we'd be able to evaluate and interpret with Vindy compared to what a lander would be able to see on the surface of Venus. And so this is a little bit of the exact type of measurements that we were able to take at AIDEN. We did 3 specific types of measurements. One was what you saw earlier, which is basically the descent from the ground all the way up to where the FAA told us we could go, and back down again with that spin rate. And that is down here on the left-hand side. Those are from the descent images. In addition, we had 2 other flight paths. We had a mid-altitude flight path that we did basically like a lawnmower pattern across the entire crater. And then a low-lying altitude path that gave us more like the ground truth, that 4 to 10 centimeter scale that you would see with the lander. And so up on the left-hand side, like the top left, we mapped out all of those paths overlaid onto each other, so you can see exactly where all of our data came from. We took all of that data and we applied compression algorithms to be able to generate exactly what we expect to receive with DaVinci and with Vindy on DaVinci. And so we expect to be able to get approximately 50 to 70 centimeters per pixel with the Vindy camera, especially within the last kilometer or so of descent. So in the middle here, in the red box, is what we expect to be able to receive from Vindy. And we compared that with the 4 centimeter and 10 centimeter scale per pixel that you would expect to be able to receive from a lander. And what we're happy to note here is that though there is some granular detail that is expected to not be able to be seen so much in the 70 centimeter per scale per pixel images, you are able to denote key features and key differences in the structures, despite a heavy compression. So to bring this back to DaVinci, we're expecting to be able to achieve somewhere between 40 up to around 150 images throughout our descent. All of these images are going to be as we descend over alpha within our expected landing ellipse. And the final 5 images or so will be the broadband imaging that we need to discern the mafic from felsic rock. And so we'll be measuring somewhere between about 0.7 microns to 1 micron, and that'll enable the composition. But additionally, all that 40 to 150 images that we'll be taking will be able to help us generate these DEMs to determine the topography that we will overlay with the compositional measurements. So what we're excited to get from this project is to help discern and evaluate what we'd be able to get from our DEMs that we measure once we arrive at Vindy. So at meter scales, many planetary surfaces are very similar. It's difficult to discern any key differences in them. But when you get to much smaller scales, obviously you'll be able to pick that out. Fortunately, what our project was able to show with these series of field campaigns is that at Vindy imaging scales, we will be able to discern many of these key differences. So in summary, we were able to conduct a series of field exercises using drone data to simulate and generate actually what we expect to be able to receive from Vindy. And what we were able to demonstrate with this is that as DaVinci is descending over Alpha Regio, we're going to be able to provide the connection between lander scales at Alpha to the larger sub-regional scales that will be measured by in a global context by our sister missions. And with that, I'd just like to leave you with the names of all of our key members and key participants in this field campaign. This does include the students that were out in the field with us. We were very excited to have them out there working with us. And I'd also like to, very much thank you to all of them, but also thank you to all of y'all for letting me present to you today.
Thank you, Erica. Our next speaker is Stephen Garland on Venus. Sorry, it cuts out the title here. Venus analog emissivity measurements in the lab and in the field using a Venus emissivity mapper emulator.
Yeah, so good morning, and again, thanks for coming out so early. I'd like to tell you today about an instrument that we've set up to emulate the Venus emissivity mapper. We call it the VEMulator. You might see VEMU for short on some of the slides. Yeah, I'd like to give a big thanks to all the co-authors on this, and especially Salma Sadeli, who basically worked very closely and did this together, but I will be presenting it. So yeah, I think I don't need to give much of a background here, but just for the sake of it, we've got 3 major missions going to Venus in the early 2030s. We know surprisingly little about the planet, about the mineralogy on the surface. This is because of Venus's very dense carbon dioxide atmosphere with H2SO4 clouds. I think that's on the bingo card as well. And this makes direct surface measurements quite challenging. But the VEM instrument, which is also on the Envision mission as Venspec M, will overcome these problems by exploiting, do I have a pointer? I think it's here. Yeah, by exploiting 6 quite narrow bands in the near infrared where there is higher transmission through the atmosphere. Yeah. Okay, so why did we build an emulator of the VEM instrument? So for us, it's important as scientists who are going to eventually look at the data from the VEM instrument to understand how to interpret it. And we only have these 6 points in the near infrared, and we need to understand what kind of information we can get out of that. So it's important to make analog measurements of realistic Venus materials. And in this context, we participated in the Veritas Science Team Field Campaign to Iceland in 2023. And as a small team, and we conducted measurements in the field with our VEM analog instrument, and obtained mainly reflectance data, so during the daytime, of analog sites that were identified. And this will be part of future work to look at that in more detail. But we had a kind of bonus because there was an active volcanic eruption when we were in Iceland. And we were able to image that flow, lava flow, as it was cooling. Unfortunately, we got there a little bit too late. And it was not active anymore, but we still got some very interesting measurements. And finally, very important that we can support with our work, laboratory studies with our new instrument. So what does it look like? It's based around an InGas detector camera, which was actually considered for the VEM instrument, but in the end, another one was selected. And so we were really lucky and able to use that. And then a filter wheel construction with 6 bandpass filters, which closely corresponds to the filters that are selected for them. And yeah, it was set up for the field and can be powered by a battery. So the first task was to calibrate the camera. So for this, we used a halogen light source integration sphere with known radiances, radiances at unknown distances. And by basically, we could construct then calibration functions for each one of the bandpass filters so that we can then convert our digital numbers directly to radiance values, which is what we want. Oh, unfortunately, the image isn't displayed properly, but okay, but here there would be an image of the VEMulator mounted actually on top of an emissivity chamber that we have in our lab, the Planetary Spectroscopy Laboratory in Berlin. And a bit unfortunate that you can't see it, but basically this is a vacuum chamber, and inside you have a system to mount ceramic cups onto which you can place samples. And in our case, we had a sample of basalt from the 2023 eruption that was collected during our field campaign. And on the surface, you have located a thermocouple to get the surface temperature, and you can inductively heat the sample. And generally, then the chamber is coupled to an FTIR spectrometer. And with that, you can get your near-infrared spectra. And in our case, we mounted our camera on top looking through a potassium bromide window, so we could image directly the samples. And luckily, one image is remaining. And this is what we see through the A60 nanometer filter. So here you see the basalt slab being heated inside the ceramic cup. We can go up to 450 degrees or even higher, but in our case, that wasn't necessary. And great, the image is there. So here you can see what it looks like when we heat up this ceramic cup. So you can see the ceramic cup here actually glowing more strongly than the sample. This is not because it has a higher emissivity than the basalt, but it's actually heated more efficiently because it's directly in contact with the steel heating plate. Here you can also see the thermocouple quite nicely on the surface. And what I'd like to also point out is the inhomogeneity of the radiance from the surface. So you see some patches are brighter than others. And that's something important and something that we need to consider during our measurements of emissivity. So the goal of these measurements was to verify our calibration to see if it's valid before we look at the field data. And so the idea was to calibrate, was to take measurements at different temperatures with our system and to calculate an emissivity, which is the radiance that we calculated or measured on our samples, normalized by the black body Planck function at the same temperature. And the temperature was this local temperature, right? And here we see experimental radiances. These are the points representing the different filters. And the bands represent a region of the black body curve radiance with a temperature spread of about 10 degrees, which is what we estimated we had over our sample in this case. And what's kind of important to consider, or one kind of take home from the presentation, is that in the near infrared at these temperatures, there is a strong temperature dependence of the Planck curve of black body radiation. And this results, if you don't know the temperature quite precisely, you get a large error in the emissivity when you calculate that through. And so here we have measurement from the vemulator on the chamber as the red dashed line, and the red shaded region is actually our error bar on the measurement. So that's something we need to try to reduce. And in black is a measurement from the standard procedure, which is used in the lab. And so, yeah, and just finally coming to the last part. So we've calibrated the camera, we set it up, and we've verified that this makes sense. And then we wanted to look at the field data. And this is actually an image of the crater at Vagra das Fjall. It's a hard word to pronounce. That was created during this 2023 eruption. And we're standing on top of a hill looking down onto this crater. For our temperature measurement, we had a thermal infrared camera, FLIR camera. Okay. And the aim was to use this as a case study to try to calculate the emissivity in this real life, quite complex scenario. And we did that by selecting different points, which so here you see an image from the camera, from the vemulator camera, and here from the thermal infrared camera. They were next to each other, so not exactly the same view, but very closely related. And you can see that the flank of the crater here matches the flank here. And we selected regions in both of these. So we have the temperature and then the radiance through these different filters. And the goal was to calculate an emissivity from this. However, we didn't get that far yet. It's a very complicated system, and this is something that we're still really diving into and trying to get to grips with. But here you see the radiance values for the selected region on the crater flank. And actually, these would seemingly correspond to a basalt with actually a lower temperature than what we measured. And the reason, a higher temperature than what we actually observed with the thermal infrared camera. And there can be many reasons for this. I think this is why it's really interesting to look at this kind of complex data. But what we might have is, for example, a coating of brighter material on parts of the surface of the imaged regions. So often it was at hotter regions where we had vents and basically outgassing and some deposits. And we also have possible multiple temperatures. So I think I ran out of time, but here's the outlook. And there's also a publication, an extended abstract on the SPIE. So please take a look at that if you want to know more, or just ask me. Thank you.
about our gap.
All right. Unfortunately, the next scheduled speaker couldn't make it. So we have a 10-minute gap. Would you like to make some community announcements?
Yes, just reminding again for everybody that wasn't here at 12 p.m. we had the Venus Community Interest meeting. And yeah, there's also a virtual Venus poster session tonight at 6:30.
If there are additional questions for the speakers or leftover questions from the Venus session yesterday that people have been holding on to, the mics are open and you are welcome to come up and ask those.
Paul Burnwashu, I have a question for Erica. Can you talk more? No, and I'm not doing this just to pick on you. Could you talk more about the actual ConOps of the taking those descent images? How many we'll get? What the highest to lowest spatial resolution is going to be? The rate? Are you expecting the probe to be turning or spinning? Are there concerns of smear? I'm just like, can you talk more about like the kinds of images we can expect to get?
If I answer this, I don't have to participate in the full 20 minutes later, right? So unfortunately, I don't have all of your answers for you. That level of detail is just not stuff that my brain holds on to all of the time. And also fair warning to anybody else that wants to ask me questions. Many of my answers are going to be, please email Jim. Oh, also, is Jim online? Can you see him in the chat? Okay, he must be in a meeting. You'd know. Because he'd already be answering everything. Okay, so we do expect somewhere between like 40, I think the answer is actually 43 images to 150, like I mentioned earlier. We begin once we descend below the cloud deck, because otherwise, not really seeing much of it. And then we take them all the way down. We do have a spin rate that we expect, and that is included in all of our activities here and we actually did simulate that with the drone itself. And we also test a little bit faster and slower, just, to cover the full band range. There is like 7 parts to that question. Did I hit the main? I mean, once you get below the clouds, we're going to be able to see them. I mean, once we get about below the clouds. You should, yeah. I mean, there's a whole bunch of thoughts about hazes, which we're working through those computations as well. But yeah.
Trevor Austin, Arizona State. Noam, you got a question yesterday, and I promised that the person online that I would ask. It's from Aster Coart at PSI. You mentioned that the inner and outer WSPR cameras have different sensitivity to the oxygen air glow, and she was wondering if you could use that to estimate the contribution of the air glow.
I think that's a great question. The answer is we're going to try. I think that the way we currently are resolving the air glow for essentially removing it to try and look at the surface is an empirical correction that's essentially a fairly complex polynomial. That is probably, and that's, so therefore it's a pretty uniform emission angle dependent solution. It will be a different solution for the same area between WSPR O and WSPR I, and we might be able to, I'm hoping that we'll be able to do something like that if we can do this over multiple images that cover the same region. The part of the issue is that if the oxygen air glow is not completely uniform over if there's like variability over the size of an image, then that will show up in the residuals, and it may be hard to determine whether it's oxygen variability or clouds of other kinds or anything like that. So we have depending on how easy it is to make that calculation, then we'll be trying to differentiate those things.
If I just really quickly, do you think it's worth sending a dedicated instrument that does more or less the same thing that WSPR does, but just in orbit around Venus and made for Venus?
Well, I think that one of the things that that WSPR has demonstrated is that this wavelength range is in fact of value, right? But I think so. I think that having this very near infrared capability, I don't know if I would dedicate an entire mission to it, but I think that an instrument or a set of adding that capability to a multispectral instrument or a spectrometer or something like that would in fact have value for both atmospheric and surface science.
Jim Cutts, JPL. Another question for Erica, which I'm sure she wants to bounce to Jim. Somewhere I read that Russian scientists characterize the lighting conditions on Venus as rather like a winter day on a very heavily overcast day in Moscow. New Mexico is not very like that. So you have direct sunlight instead of heavily scattered sunlight. Also, the area is thin, and so you don't have really scattering. Has that been factored in at all into these simulations?
In this campaign, no, although we did have a couple of jokes about we were hoping that the desert was going to allow us to have an overcast day, and of course it never did. But it was not done for this because we were looking at a separate aspect to what we're going to be able to generate with the Vindy measurements. But that would be an ongoing procedure going forward to put into more of like the modeling component of it.
Okay, we have 2 minutes left. Any last comment, question, or remarks? General, Norm, do you want to say anything good about the meeting, etc.?
Sure, come to the meeting. So at noon we're going to have, as you all know, the assessment groups are still shut down. If you were at NASA night, we know that NASA is working on getting us turned back on. It could be imminent in the next few days that we'll hear about this, but instead of having a town hall, a VEXAG town hall at noon, we're having this Venus community meeting. We will have a report from VEXAG, and we'll also have at least basic status reports from the 3 major missions, and a quick report from VESCOR. But by and large, that meeting is going to be at least half open mic. Since we are not doing ag business, we can talk about whatever we want. And I think that we have a lot of things to share as a community. And I think, and this is part of the question, like what now? What do we do going forward as a community, as an ag, in the current circumstance? And I know we've all been thinking about this kind of thing. So, and one of the things that I'm extraordinarily proud of about the various science communities, but the Venus science community in particular, is, over the last decade plus, the community has shown a massive scientific and scientific cultural unity in order to get the things done that we've been able to get done. And I think that is something, no matter what is going on at NASA and anywhere else, is something we want to preserve and even strengthen over these couple of next however many years. So I'm hoping that that'll be part of what we talk about at this meeting. So
Perfect.
Please do come.
Your time's up. Thank you so much, though.
Now I'm done. Okay.
Our next talk is by Sarah Port on 60-day mineral weathering experiment in the NASA gear, implications for Venus volatile cycle.
Okay. Good morning, everyone. I hope you had a great coffee break. My name is Sarah Port. I'm currently a postdoc at UTSA. But before this, I was a postdoc at NASA Glenn Research Center, where I studied mineral weathering on the surface of Venus. And so I'll be talking about some of those results today. So everyone here is familiar with the idea that Earth and Mars, at least some point in its history, had liquid water on its surface. But what about Venus? So Venus and Earth have a similar radius and bulk density, and models have suggested that the volatiles in water on Earth may have been delivered during a late stage accretion period, and Venus may have been similarly affected. Now we know Venus today is very dry, right? 30 ppmb in the atmosphere. But in situ measurements by the Pioneer Venus have measured the deuterium to hydrogen ratio and found that it is 100 times higher than that of Earth. That suggests that Venus could have had liquid water on its surface at some period in time, but over time that lighter hydrogen was stripped and lost to space, leaving behind that heavier deuterium. Now, some 3D climate models have suggested that Venus could have been temperate for quite some time and hosted liquid water on its surface for a few billion years. Now, this begs the question, if this did happen, did minerals that normally form in the presence of water have formed? And if they did, would they be present today? And this is a critical question to address, because if we can identify them on the surface, that can inform us on the past and current water budget. Okay, so we tested a series of different minerals to address this question in the GEAR, the Glenn Extreme Environment Rig, located at NASA Glenn Research Center. This was a 60-day test, and you can see on the right-hand side all of the gases that were used in this test, the initial gas compositions. We have everything from CO2 to SO2 to HF. And in the bottom right, you can see the temperature and pressure during this test. Now, in this presentation, we're only going to focus on 6 minerals: calcite, magnesite, siderite, phlogopite, muscovite, and brucite. And they've been exposed as powders or slabs or both. We use a slew of different analytical techniques. And in this presentation, I'm only going to focus on CHN analysis here, XPS, FTIR, ATR. And we also actually use some FactSage, it's thermochemical modeling software, to model some of our results. So here are our samples before exposure. And this is what they look like after exposure. And you can see that they all did exhibit a color change. Our powders also changed in color. They became more of this sort of dull gray after exposure. And we also saw some changes in mass. We see brucite lost the most amount of mass over here, 3.1 milligrams. We saw some minerals, such as phlogopite, that gained mass, 0.05 milligrams. Now, using XPS, we were able to analyze the change in sulfur abundance and fluorine abundance, as seen here. And what we see is calcite and siderite had the largest change in sulfur abundance. We did identify sulfur minerals in both. And phlogopite, muscovite, and brucite had the largest changes in fluorine abundance, and magnesite exhibited the least amount of change. So now I'm only going to focus on the hydrous minerals. So this is using CHN analysis. We measure the carbon weight percent. And you can see phlogopite and muscovite before and after the experiment, not really a change in carbon abundance, but brucite did. There was a change of 10 weight percent of carbon. Now, when we look at the brucite powder using FTIR, ATR, we can see in the control that's before the experiment this very prominent peak of OH. But after exposure, the top of the crucible and the bottom of the crucible did not have any OH. And when we look at CHN analysis of the hydrogen abundance as well, we see that after exposure, we do see a drop in hydrogen abundance. Now, we did model this in FactSage as well, and what we found is that when we start with brucite and expose it to Venus temperature and pressure, but not the atmosphere, it does dehydrate, but when we expose it to Venus temperature, pressure, and atmosphere, we see that it forms magnesite. Now, this is interesting because we also tested magnesite in FactSage, and we found that when we expose it to Venus conditions, it did not change. It did not interact with the atmosphere in any way. So it seems stable. And so based on our experiments, FactSage modeling, we conclude that when brucite is exposed to simulated Venus conditions, it will dehydrate, releasing water, leaving behind MgO, which can now interact with all that CO2 in the atmosphere to form magnesite. Now, here on the right-hand side, we have a table summarizing some of our results, including if it could potentially be a water indicator. Now, magnesite could potentially be an indicator of past or current water. Why is this? Well, magnesite generally forms in the presence of fluid-rich planetary environments. And from our experiments and models completed by us and others have found that if you have magnesite on the surface, not the highlands, at the surface of Venus, if you expose it there, that it is stable. It doesn't interact with the atmosphere. And so if we were to identify it on Venus, it could potentially indicate passive current water. Now, of course, we do need to be careful here. We do need to identify other possible avenues of magnesite formation. So for instance, carbonatite lava flows has been suggested to explain like the canali, right, the sinuous channels on the surface of Venus, and carbonatite can have magnesite. Now I want to go back to the XPS figure I showed you earlier, and I want to focus on phlogopite and muscovite. So as I said, we did see a change in fluorine abundance for both, and actually this is the first time that we've confirmed the detection of fluorine minerals in a Venus simulated experiment. So what is happening here is actually the HF is attacking the lattice bonds, replacing the OH and releasing water, forming fluorine. As you can see here, the OH being replaced by fluorine. Now, what's exciting about this is because experiments have shown that fluorine-bearing versions of phlogopite and tremolite, which is another mineral, it's also got OH in its crystal structure. But what they found is that these minerals are more stable than the OH version at high temperatures relevant to Venus. And so we were also interested in understanding how studying these volatile cycles even more and how they could affect the atmosphere and the surface and vice versa. And so we took this equation, which is phlogopite plus HF equals fluorphlogopite and water. And we wanted to see how that would affect water and HF abundance. And so just looking at this reaction, just this one, if we assume that all of the HF in the atmosphere, which is 5 ppb, is interacting with phlogopite, we found that it really doesn't change the abundance of water in the atmosphere, which shouldn't be surprising, right? There's not that much HF in the atmosphere to start with. And that actually to react to all of that HF, it's about 0.2 volume percent of the crust needs to be phlogopite. Now, if we were to dehydrate phlogopite, HF is not involved. We just let phlogopite dehydrate completely. We find that if we start with that 0.2 volume percent, because it was in the previous slide, we find that the total H2O only increases by 0.5 ppmv. Remembering that in Venus, it's 30. And if we were to just go to 1 volume percent, we find that it increases by 2.4 ppmv. Now, how quick does this reaction occur? Well, experiments have shown that phlogopite completely dehydrates, releasing all of that water in 3 billion years. And so if it takes that long, we can already expect that it wouldn't be releasing that much water in the atmosphere per year, you know, from these calculations, 10 to the 3 to 10 to the 5, knowing that in Venus's atmosphere, it's 10 to the 16. Now, once again, this is just these equations, these two reactions that we studied in this presentation that we're showing in this presentation. And this does not include any other inputs such as volcanic inputs. And we're actually working on those calculations right now to better understand these sort of volatile cycles on Venus. Okay, good on time. All right, so here we have the final table. This shows a summary of all of the minerals that we tested. Well, in this presentation, we have more minerals that we tested. And so can fluorine micas inform on Venus's water cycle? So we did see the formation of fluorphlogopite in our experiments and fluor muscovites. And we know from experiments completed by others in modeling that fluorphlogopite in particular is more stable at these higher temperatures, these Venus relevant temperatures than OH. Now, fluor muscovite has not been investigated, but muscovite has. And modeling completed by Zolotov 1999 and Simprick et al. 2020 have shown that muscovite may or may not be stable. It does depend on your starting conditions as well as the elevation on Venus. So fluor muscovite is still a possibility. And we did see in brucite and in phlogopite after 60 days dehydration. And in our crucibles of muscovite and phlogopite, we actually saw changes in colors with depth. And phlogopite in particular, we actually had less OH at the top of the crucible than at the bottom of the crucible. And what this suggests is that mineral stability is also tied to dehydration. And so we really need to understand the rate of diffusion and dehydration to critically understand passing current water budget on Venus and understand these minerals over time, their stability over time. Thank you.
If the other speakers, Erica and Stephen, can join Sarah on stage for the Q&A, and you can also start coming to ask your questions.
And just a reminder to please state your name and affiliation when asking questions.
And people online can also ask questions.
Yes. Hi, my name is Guus Aert from Delft University of Technology. I have a question for Ms. Poort. You mentioned that the magnesium carbonate is stable on the surface, but the other carbonates aren't. So calcium and iron sulfate or iron carbonate. Why is that?
Okay. That is a great question. Well, calcium and the iron are definitely more likely to react with the sulfur based on just the sulfur abundance. So the SO2, the fugacity, is playing a critical role here. And so magnesite has just been found based on the SO2 that's found on Venus to just not be as likely to react. So you would need even more SO2, I think. I don't know how much more, but.
Yeah. And if I may, second question. You ran the experiment for 60 days, right? Why did you choose 60 days? And would you expect different results if you had it for a longer or shorter time?
Yeah, so 60 days was the scope of the proposal. So it was one experiment, but I would love to do experiments for a longer period of time as well as shorter periods of time. And so actually the plan is in the future to do more experiments so we can better understand that rate of dehydration and interfusion, as I mentioned.
Yeah. Thank you.
Maitri Bose, Arizona State University. I have a question for Erica. With your images that you took, you probably took them, what time of the day was it? And can your imagery be corrected for, the shading effect in any way?
Yeah, we went to 3 different sites, but on average, we took our images somewhere between 10 a.m. and 2 p.m. And that was chosen to minimize the amount of shading that existed out there. These sites also were selected due to the minimal amount of vegetation as possible, to try to also minimize any sort of like outliers that we would not expect to see on Venus. But yeah, it was taken as basically as close to noon as possible.
I have a question for Stephen. At some point, you mentioned that you're trying to reduce your instrumental error, so the uncertainty on your measurements. Can you expand on that? What are the main sources of uncertainty on your measurements?
So I wouldn't say so much the instrumental error, but it's more a question, or the main problem that we've identified so far is to constrain the temperature when we're trying to estimate the emissivity. So we're in kind of an unfortunate part of the Planck curve when we're looking at the Venus surface with VEM. So a small change in the temperature leads to a large change in radiance values, basically. And so that's why it's very important to get more accurate temperature measurements. So that needs to be looked at in more detail in the field measurements, but also potentially in the lab when we do see, not always, but sometimes temperature or radiance inhomogeneities across the surface of samples. Yeah.
Allison Santos, Wesleyan University. Surprise, my question is for Sarah. Could you just, my download rate is not fast this morning. Could you just walk through again how you were doing the Flogopite water budget calculations again? Sorry.
Yeah, no, it was a very straightforward calculation that we're doing right now where we know that how much HF there is. If we assume that HF is only reacting, it reacts to completion, and then calculating the number of moles, knowing how much that's in the atmosphere, and then calculating then how much that would be on Venus, and starting from there. And then, sorry, I did another calculation where I looked up how much Flogopite is normal on a planet, but no, this was solely just based on the HF abundance and calculating straight through.
And so the the gas abundances you're taking for the planet, not
Yes.
the experimental environment.
No, not from this.
Okay.
So this was, yeah, sorry, I should have clarified for the calculations were all for if on the surface of Venus. Yes. Mhm.
Okay, awesome.
Yeah,
Thank you.
yeah. I'm really excited because I've also looked up how much HF usually is ejected through volcanic activity. And so I want to do that to try to understand budgets over time. And so I've done some of those calculations. So I'm excited for that.
Nice.
Hi, Salma Zadeli from DLA. I have a question for Sarah. It's actually a general question about the gear experiment. I wonder, how do you deal with contamination? Thank you.
Sure. So what do you mean by contamination? Like, what do you like interactions with the gear vessels or what are?
With other samples that are in the same vessel.
Yes. So that's a great question. So there were in that particular test, there was actually quite a number of samples. And so Allison Santos had some samples in there as well. A number of other people in the audience did also. And so we have been communicating about things like that. Now, on top of that, there was, which is Allison's idea, which is very intelligent, brilliant idea, really, is on the tray where we have all the samples, we had quartz, pure quartz in all four corners to see, because they should be unreactive. And so if there's any changes in those or different contaminations, different minerals or something that could have like wafted onto them, we could easily identify them. So that's how we've tried to identify that. In terms of like, we also measure the gases every few hours so we can see how the gases change over time and we can boost it if there's any changes so that we can keep it to Venus conditions.
So I have a question for Sarah. I was wondering why those 6 minerals that you picked?
Yes, so I had 35 minerals and I chose these 6 minerals for this particular presentation because we got the, I think the most interesting results from the 6 different minerals. And they were all very excited because they are all relevant to water, right? So carbonates, for instance, for the most part, you need fluids. You don't necessarily always need fluids, but it definitely highly facilitates the formation of carbonates. And then as well as the micas as well, right? Because of the OH. So you do need volatiles as volatiles there as well. So it was, we were really interested to see just how they would change if they dehydrated, if they altered, and what that would mean for Venus. If we were to go back, what should we be looking for?
Okay, we have an online question from Arwen Abbott, LPSC ambassador, I think for Erika. Were there other terrestrial sites considered for this study, and what made AIDEN the best analog for Venus surface compared to those alternatives?
Yeah, there are several analog sites that we'd like to do going forward. One is a couple other sites in New Mexico. We chose New Mexico for multiple reasons, not just because of the scientific analog itself, but also because we wanted to include the team out there that we've been working with. And in addition to New Mexico, though, we've been looking at a bunch of different sites, including Iceland, of course, and working with the Avengers team to look at other Venus analogs to as we go forward with this project. Right now, this was basically just like a really quick sort of had the opportunity to conduct these drone tests. But we are generating right now several proposals to be able to go look at future sites.
I have a naive question for Stephen. So as far as I understand, there is still a mismatch of the temperature that you get from the field and from the lab, right? Or
I wouldn't say it's a mismatch of the temperature. So I would say so there's 2 separate parts of the work you can kind of consider separately. So the issue with the lab measurements is that we have just one local temperature measurement from a thermocouple on the surface. And because there is a strong radiance variation across a sample, which is not only attributable to compositional differences. And so there is a temperature gradient through across our sample, and that's something that we have to consider when calculating the emissivity from something like that. It's not the case for all samples, and depends also how the sample is coupled exactly to the ceramic cup. it's also worth mentioning that it's under vacuum, well, at 0.5 millibar approximately. So convective heat transfer is not very efficient. So you're really relying on like mechanical coupling to the ceramic cup to heat your sample. And that depends how your sample is. If there are cracks, then maybe also the thermal heat transfer is not so good. So yeah, in the future, in that respect, I think it's very important to consider sample preparation in terms of the thermal coupling of the sample to the sample cup, which is being heated inductively, and also to investigate to use such measurements as standard to check that you have a uniform temperature, to check that you have a good temperature estimate in that case. And from the field measurements, it's much more complicated. And I think that's why it's also interesting to take a look at it, because yeah, I kind of run out of time for that part of the talk. But what we see is that the hotspots on this cooling lava flow, they actually often correspond to cracks inside, so like looking inside the lava flow, where gases are escaping, and around these cracks you often have deposits of brighter material, possibly sulfur. So it's kind of fumarolic, and that obviously has then a different emissivity to the basalt, which is what we're expecting, what we're looking for, and so that's a possible effect. And also we do expect that there are strong temperature gradients around, on the surface. So this is also very different to Venus, right, where we don't expect it to be the case, but still it's interesting to look at it on this scale. Yeah.
Hi, Cass Nicely, University of Alaska Fairbanks. Great talks all around. My question is for Sarah, though I'd be happy to hear from the other speakers and really just anyone in general about this, because it's probably a question that doesn't have an answer yet. I'm wondering what you can tell me about, or to whom you can direct me about, what effect the conditions and presence of liquid carbon dioxide might have on likely Venusian rocks, and specifically what kind of like secondary mineralizations we might be able to see with remote sensing, and if they would survive to today through the current Venus conditions.
So what do you mean by liquidized CO2? Because on the surface, it's super critical.
Oh yeah, well, I have this kind of crazy hypothesis that I'm trying to work with Stephen Kane about there possibly being liquid CO2 rain during some time in the past, like when it went from, kind of Earth-like conditions on the surface to what we have today. It's super unlikely, but,
Yeah, I mean, so, on Earth, we study carbon sequestration, right? And so there are people who study carbon sequestration where they inject fluids and CO2 mixtures into, to see how it would interact if it was injected into deeper into the crust to see if they can, remove CO2 from the atmosphere, right? So I think that would be similar, I would imagine, like experimentally then, that you can like apply those experiments to understand how it would change. I mean, if you have more CO2, then you would probably get more carbonates and things like that, those types of minerals. So it's my hypothesis. I don't know if anyone has any other. No.
Thank you.
Yeah. It's not just chemical.
Question for Stephen, as somebody who has also done field work in Iceland. I was wondering if you could comment a bit about the process of field hardening your instrument against dust and the being dropped and other various things.
Okay, well, so it was dust proof, but not really waterproof. Let's say water resistant. So we had to be a little bit careful there. Actually, we were incredibly lucky. So for the time that we were there, I think we got rained off basically 2 times. So I think it could have been worse. But yeah, we basically, the idea was we have to be careful. We have to look at the weather, and when it starts to rain, it can take a little bit of rain. But if it gets heavy, then no. And everything was contained inside a dustproof box, and the fans had filters on it. So from that perspective, it was okay. Yeah, there was one time sort of when we're in central Iceland, and we wanted to image the active eruption and heard that it was stopping and cooling down. So we rushed back And the first night that we walked out there to try to make observations, we got to this hill overlooking the crater, and it just started to pour with rain. We walked all the way back. So that was a bit unfortunate, but yeah, otherwise we were quite lucky.
Still on field campaigns, I for Erica and also for Veritas, like what are the next plans for field campaigns if there's already things lined up and so on? If you can comment on that.
For us, I sort of answered that earlier. We have ideas that we're trying to make come to fruition, but it's mostly trying to identify other analog sites that would be useful for us, that also, try to involve a little bit more of some of the questions that the audience asked earlier. That's going to, maybe not be a bright, everything perfect sort of day, because we definitely did not have to deal with rain in the desert, for example. But we're working through some of the future directions we want to take with our project.
For Veritas, I'm not really the right person to to say, I think. So please ask my colleagues. But
Sue can
yeah,
comment. I
Sue.
think she's coming.
Yeah, so the 2023 campaign, we planned with DLR and their FSAR plane and to acquire the X and S band data there. And so we're working through all of that analysis and looking forward to writing some papers hopefully this summer. But we would like to, there are things we'd like to revisit in Iceland to increase the range of the radar parameters that we have obtained so far. And additionally, there are other sites that we would like to go to, but so far it's a question of funding. But we'd like to go to other types of tectonic sites with the field campaign. But likely we'll go back to Iceland soon.
Thanks. Any more questions? If not, let's thank our speakers again. And we can just a few more reminders. If you are going to talk in the next blocks, don't forget to get mic'd up. If you're judging for the Dvornik Award, don't forget to do that.
And sign up.
And sign up for it. There's still time. Yeah. And yes.
Hello, we have 1 minute for an announcement. So I thought I'd draw your attention to a new Venus book, which is out. If you're wondering what to get all your friends, families, colleagues for Christmas, New Year's, anything, get in there early. The book is called Venus Evolution Through Time, and it is the product of over 100 authors. It's an ISI workshop, International Space Science Institute workshop. Editorial board included Thomas and myself, as well as familiar faces Sue Smrekar, Doris Breuer, Tilman Spohn, and Cedric Gilman. And the idea was really to try to have a synthesis of the current state of knowledge and modeling on Venus evolution, and also a look forward to what we hope to be able to settle with the next set of missions. So have a look, Google it. This is the worst advert ever in that I don't have a book to show you right now, but it's available at all good bookstores. Thanks.
All right, and just a reminder that we will have another block of 4 talks followed by a Q&A for all the speakers. And with that, leading off in this session, we have Matthew Weller, who will be talking on Venus, tectonics, atmosphere, and climate. Oh my.
All right. Hello, everyone. I wish I had known you were plugging the ISI book. I could have put it up on the title slide so everyone could have seen it. Yes, I will be talking about the evolution of Venus. I notice I changed the title ever so slightly. This is the story of Venus, the planet. Not really, but let's go ahead and move forward. All right, some observations that we do know for Venus. We should mostly all know these, but it's worth refreshing our memories. The atmosphere is approximately 90-93 bars, overwhelmingly CO2, with a small helping of nitrogen as well. High surface temperatures, we do know that. The surface of Venus is relatively young, anywhere between 1 billion years to 200 or so million years old. and is predominantly volcanic, at least 80%, probably more. Volcanism is estimated to roughly intraplate levels for the Earth, so it's about a cubic kilometer per year. And there's no evidence of plate tectonics, with a caveat. Now, at least. That's not necessarily the case that there wasn't evidence, and we'll talk a little bit about that. So, key point here is from physics and the last decade, a lot of work that's been done, tectonics can and should be expected to change over time. With that in mind, we can take a look at these observations and recent work that I've done that actually suggests that Venus's atmosphere really records an early epoch of early plate tectonic-like evolution. This comes from 1D parameterized models. We can take the next set of observations and tie this with 3D tectonics and convective models, that Venus really surface and atmosphere can be explained by a transition. So we start plate tectonic-ish, like transition out of that to the current state. And if we couple that with the ideas from recent GCM modeling that Venus may have been habitable, may have had low surface temperatures in the past, we're left with the idea that Venus has changed relatively recently. I say that in quotes. Geologically recently could be billions of years in time. And this is fundamentally what we're going to look at. So what we're doing here is we're playing with boxes. We're playing with a box of the interior, mantle tectonic evolution. We're playing with boxes of the atmosphere, outgassing and photochemistry. We're playing with boxes of climate from global climate models. So what do we do with these boxes? We put it in a bigger box. And a lot of pain happens. Joking, not really. So what we're using is the interior to drive the atmosphere evolution, to drive the global climate model iteratively. I would draw arrows here, but we'd be here all day to show you what I'm doing. So let's jump into the 3D models. Here's an example of geotectonic model, evolution, temperature field, surface conditions, 3D models, outgassing here on the bottom axis in cubic kilometers per year over about 2.5 gigayears. And these are multiple examples that we're showing. We're going to couple this to a volcanic outgassing model. That's the Guy-Arden Scale A model, which is, in this case, fixed oxygen fugacity, upper mantle of the Earth, and pressure dependent. And we're going to allow it to evolve to Venus-like conditions from an early Earth-like state and see if we can use these 3D models of mantle convection to create Venus. Here's an example of the outgassed atmosphere. This is an outgassed only end member right now. So we have several different cases. You see a case right here that generates substantial atmosphere, cases that generate pretty substantial atmospheres as well. It's a range of conditions. The important part to remember here is that they're just different initial conditions. This is actually higher surface temperatures to start with. So we start with a plate tectonic-like phase down here. This is roughly equivalent to what we see on the Earth now, where we generate about 0.4 to 1 bar over around 200 million years. And we allow it to evolve through this transitionary step. This is that step-like function where you have large jumps. We can generate 3 to 20 bars over 60 million years. And this is an important part of this. This is stochastic. We get a large number of these and they vary in time and space. And then we hit a single plate phase where volcanism really gets quiescent, and that happens for about 1 billion years. The key point here is all of these cases are qualitatively similar. They can generate tens to hundreds of bars, even based on a slew of different assumptions. They all kind of show the same behavior. So we're going to use these results and process them using a 1D photochemical model, Atmos, and a carbonate silicate weathering cycle. And we're going to use that to update to drive the GCMs. And then we use the GCMs to update the 1D chemistry to drive again the GCMs. So we iteratively evolve these. So here are some examples. We have an aquaplanet that's pure water around the planet, no topography, 10-meter ocean, like a bathtub ocean, and then 310-meter ocean, Venus topography. Surface temperature is here, red is warm, cool is cool colors. And our surface temperatures are plotted here for the epoch at 2.84 gigayears ago. Key point to notice, the aquaplanet is ice-free at this point in time. The 10-meter ocean has ice caps, but we have fairly substantial glaciation possible in the 310-meter case with Venus topography. Now let's evolve this in time. This is outgassing. And photochemistry of the atmosphere. We now go to 2.7, temperatures drop a little bit, which is interesting. But key points again, aquaplanet's kind of boring, ice-free. We have much greater ice cap extent here in the 10-meter ocean and a lot more glaciation in 310 meters. But notice we are dropping some 10 to 20 degrees Celsius over that few 100 million years. And that's kind of interesting. Outgassing is increasing, but surface temperatures are dropping. And that's actually a nonlinear response. We think it's coupling with the ocean. Now we evolve it again, and that nonlinear response changes. And again, aquaplanet here, knows ice-free, refrained is kind of boring. Ice 10-meter case, ice is limited, which is interesting. And we still have glaciation here. But if we allow it to evolve again, we get something interesting. The aquaplanet is rapidly running to a runaway or moving to a runaway state. The 10-meter case is generally pretty unpleasant. The 310-meter case, really you have glaciers in Ishtar. That's about it, but it's still relatively temperate. So the question is this 310-meter case our last best hope for habitability of Venus? Kind of looks like it is. And the answer is, well, maybe. It turns out that there's an interesting caveat here. So let's jump into this. So what we did is we took these results and plugged them into the planetary spectrum generator to look at what the outgassed atmospheres will look like. Don't worry too much about what those colors actually mean. Just know that this is time and composition. So blue is earlier in time, less outgassing. Red is much more outgassed. You see features getting broader. What you'll notice is the bulk atmosphere has water in it, some CO2 and maybe some CH4, which is kind of interesting result. But that's not what excited us. When we took a look at what sulfur is doing, especially when we get to higher levels of outgassing, we are actually generating sulfur hazes. So these are hazes like potentially the Archean Earth or Titan. So this is strongly suggesting that Venus might have been a haze world as it's undergoing this transition in tectonic states and this evolution of its climate, which actually has some substantial effects on moderating the climate. So work done for Mars suggests that sulfur aerosols can reduce the climate by some 20 degrees C, depending on where they're input into the system, how long they persist, et cetera, et cetera. The other key caveat here is this outgassing is highly variable. We might not actually be getting peak outgassing, and this is going to be fundamentally tied to outgassing. So we're generating hazes. We don't really know how prevalent those hazes are yet. But the important part here is hazes really aren't accounted for yet in our photochemistry model, nor in the GCMs. And that is something we need to think on and start pulling these threads to understand exactly what effect these hazes are. But this can be really important when we're thinking about Venus, particularly as an exoplanet. Bingo card, everyone. So, conclusions. The goal here is really to couple the interior and surface to the atmosphere to Venus. We're trying to understand Venus, the planet, like Spaceballs the movie. That's a deep cut for anyone who remembers. So transition in tectonic models can match many observables. There are ways we can get there, and these are very non-unique solutions. There's a lot of different solutions that can match what we see. But we can generate Venusian atmosphere over roughly 2.5 gigayears. That comes naturally out of these models, and it happens through punctuated events. Habitable conditions may not be a straight line, and that's really important for Venus. It really depends on surface water inventory and topography for climate evolution. But hazes are a detectable output, and that is something we really need to start thinking about in these models and in terms of habitability of Earth-like, Venus-like systems. And finally, with the last 10 or so seconds, just a quick plug. You like what you see? I'm looking for a postdoc. Please take a look. Send me an email. Let me know if you're interested. I'm interested in talking with you, and I am perfectly on time. Thank you, everyone.
All right, thank you. Next up, we have Lauren Ratchford talking on comparative structural mapping of highlands on Venus and cratons on Earth.
All right, hi everybody. I'm Lauren Ratchford, and today I'll be talking about some work I've been doing at Washington University in St. Louis with my advisor, Paul Byrne. So the first thing that I notice when I look at our beautiful globe here on the left is our massive continents. Not only do they visually stick out from our ocean basins, but they are also plateaus above our ocean basins. And similarly, when I look at this beautiful topo map of Venus, which we've seen a few times now, what stands out to me is the highlands. And this here is Aphrodite Terra, which is Venus's largest highland. So on Earth, our continents are formed through plate tectonics processes. The cores of our continents are called cratons, and over time, terrains are smashed onto those cratons and build up to our modern continents that we see today. But what about Venus's highlands? So there's been previous work in the highlands of Venus. Chadwick and Schauber had a 1994 LPSC abstract where they looked at Alta Regio and they found some crustal blocks that appear to have come together over time. And then more recently, Gilmore and Head in 2018 had a very nice structural paper where they looked at Tellus Regio, and they found different tectonic fabrics that are consistent with these areas possibly once being separated. So I think based on previous work, it's evident that there are tectonic fabrics within the Venus highlands, and that is consistent with there being these crustal blocks which may have come together. They may have different deformational histories. But what I'm curious about is how did those blocks come together? And are the structures within them consistent with continental-like formation? So I'll be looking at this question in Aphrodite Terra and comparing Aphrodite structurally with continental building areas on Earth. So if we're gonna compare the highlands with continent formation, we need to know about continent formation. So I'm sure you've all seen this before. It's like intro geology textbook level. But on the right or on the left here, we have a continent with a thickened lithosphere. This is a strain ellipse, which is now a circle, but we'll see it later again. And then over here, we have an oceanic slab subducting beneath this continent. As it subducts, it's causing arc magmatism on the surface here. And now here, much later, this is at time 2, subduction has stopped as continent-continent collision has occurred here. You can see the strain ellipse is now an ellipse. So there's been a high amount of strain here, even more thickening. And now our continent is made up of several slices of different terrains that have been added onto it over time. And these two continents are connected by a suture zone. This suture zone is basically a really massive thrust fault or a bunch of different thrust faults, but it accommodates a very high amount of strain and a very large amount of lateral motion in this tiny little area where an entire ocean once was. So here are some key features of structural comparison that I will be using. I will be comparing Aphrodite Terra to Northern Africa, and that's mostly because North Africa is a very geologically old area. It has Archean and Proterozoic crust and many well-exposed suture zones that it's been built over the entire Proterozoic. So here are 3 things that we see in North Africa. The first in pink is discrete crustal blocks with highly deformed edges. These are our cratons or bits of cratons that we're adding up to over time. The second is large-scale suturing thrust faults at the margins of these crustal blocks. These are the sutures we saw in the last figure. And the third in cyan are tectonic fabrics. So our cratons are built and they have their tectonic fabric, and then things are added onto them, possibly from different parts of the world that were formed in different situations. So we don't necessarily expect these cratons and what's added onto them to have the same tectonic fabrics. All right, so we'll start with Africa and then later we'll see if Aphrodite has these same things. So this is a picture of northwestern Africa, and here are the Atlas Mountains in southwestern Morocco, and here are the Canary Islands to orient you. And I'd like to draw your attention to this thing here in the middle. This is a known crustal block that formed Northern Africa and acted as a single structural unit. So here I've drawn on some folds that have been mapped previously, and you can see they very well outline this thing. You can see the mountains up there. And then here is the large-scale suturing thrust fault at the northwestern margin of this block. This thrust was formed when Laurentia collided with northwestern Africa, and formed the Atlas Mountains. And unfortunately, Laurentia has rifted away and formed the Atlantic Ocean. So we can't see it anymore, but if it was here, you would see the Appalachian Mountains on the other side. And finally, in cyan, here's our tectonic fabrics. These are going northwest to southeast, and you can see that what's going on inside this block is not necessarily what's going on outside of it. And interestingly, these things are actually suture zones themselves. So over here, this is Archean crust. This is Paleoproterozoic crust 2 billion years ago. This was formed, it settled, and now it acts as a single structural block. And now we'll look at Venus. All right, so here is a Magellan right look radar image of Venus. And if you haven't looked at radar, this lighter area is, you can think of like exposed rock. Here it's topographically high, rough, and these darker areas are topolows that are maybe infilled with lava or sediment. And here I've drawn on those folds again that I can see at this map scale. Tons of folds over here, tons of folds over here, a couple big bounding folds here. And here are those, what I assume to be are the large scale suturing thrust faults. These are the edges of hanging wall anticlines that I think are verging right. The dip direction doesn't necessarily matter so much as the fact that these are bounding thrusts. And here we have the tectonic fabric in the center of this block. So these are lineaments, depressions, and extensional features, but I think it's pretty clear that what's going on inside here is not necessarily connected to what's going on outside here with these trending northwest, southeast folds compared to all of this that's going on in here. Okay, and here's a comparison of the two. I think this is pretty clear, but what I'd like to point out here is that the scale, this is about 300 kilometers north-south, and this is about 150 kilometers east-west. This is Venus, this is Earth. These things look really similar visually and structurally. So I think now we can fill out the rest of our table and check off all of these 3 things for Aphrodite Terra. And this is pretty good evidence that it might have formed by continental collision-like processes, but this is definitely not definitive evidence. So my future work is going to be more detailed structural mapping and then doing field analog work on an analog site on Earth, and then doing some structural mapping and finally quantitative comparison of the 2 sites. So what if we do all this work and find out that Aphrodite Terra did form by continental-like growth? I think that that means there has been very large-scale lateral motion on the surface of Venus at some point in the past. And I'd like to make it clear, throughout this talk, I've been talking about the past, not about present. This is not happening in the present, probably in the past. So in the past, there's been large-scale lateral motion. And if there has been large-scale lateral motion between blocks, we can presumably say there was something once between those blocks. So as these blocks have come together, whatever was between them has been destroyed in some way. And finally, if it has seen this continental-like growth, then we could use Venus as an analog for Archean Earth when Earth was first building its continents. And that is all I have. Thank you.
All right, and if you can walk slowly up to the microphone because we have about a minute between talks. Our next speaker is Julia Maya, talking on constraining the interior structure of crustal plateaus on Venus.
Yes. Okay. Hello, everyone. Very happy to be here. Today, I'm going to be presenting the work that was mostly done by Jacopo Baccarin, who is a master's student that did an internship with us at DLR. And this work had the goal of understanding what we think we could get with the upcoming Veritas and also Envision, like the upcoming great gravity data that we're going to get in the future, and what we can learn about these very interesting crustal plateaus that we already heard a bit about in the previous talk. Okay, so these regions are large, like 1,000-kilometer large features. This specific one is alpha, and they have this high elevation. They have this positive small gravity anomaly associated with it. It has this very tectonized complex terrains that we generally call tessera. And also, most recently, after Venus Express, we found that at least alpha is associated with this low emissivity anomaly that could indicate that they actually have a different composition in comparison to the surrounding basaltic plains, maybe probably a felsic composition, more silica rich. And so all these pieces together, that as we're seeing, are indicating that they could be analogs formed in similar ways as continents on the Earth. And for example, on Earth, we know that continents have, for example, larger crustal thickness and some specific geophysical properties. And we want to understand also from a geophysic perspective if these regions are also pointing out, it's the geophysical properties are also pointing out to a kind of continent-like formation. So this, of course, has been looked in the past for like 2 or more decades as soon as we had gravity data. And it was very clear. So this is just the year of the study and the crustal thickness estimates. And well, data evolved and techniques evolved, but overall, we kind of reached the conclusions that these regions are close to an area isostasy state, and they have thickened crust with respect to the surroundings. But we still have very large uncertainties. I would say that now we know that we probably have a crust of 15 to 35 kilometers. But we don't know much more than that. And what we want to know is how these future high-resolution gravity data sets will help us constrain the interior structure of these features. And specifically, what we want to look here, if these geophysical investigations can help us determine the composition of the plateaus, since we can constrain density with gravity analysis, and different rocks have different densities. Okay, to do that, we're going to use a very well-known flexural loading model. So the basic principle of this model is that the topography acts as a load on the surface, and the thickness of what we call the lithospheric elastic lithosphere will say how much deflection the load will cause on the crust and lithosphere. So if you have a very thick elastic lithosphere, you're going to have less deflection and a larger gravity anomaly, while if you have a thin elastic lithosphere, you have more compensation, and this is also going to affect your gravity signature. So we can play around with testing different parameters such as the elastic thickness, the crustal thickness, and the crustal density to see which kind of group of parameters best match the observations of these features. So I showed these little diagrams on the spatial domain, but what we actually look into is in the spectral domain. So we decompose this in spherical harmonics. And what I'm showing here is the model, is what we want to model, which is called the admittance, which is how the amplitude of the gravity field varies in comparison to the topography, and how this varies with spherical harmonic degree or wavelengths. So you don't have to memorize all that, but we can clearly see that here, this admittance is really, these curves are really changing if we change this parameter for the elastic thickness, the crustal thickness, and for the crustal density. And what I'm showing here is the current global resolution that we have from the Magellan data. And if we focus here in the crustal density, we can see that at this point, the data we have, we cannot really distinguish between different crustal densities. It's very challenging. But if we start getting higher resolution, like more spherical harmonics, we might be able to start constraining that. And that's what we want to look into. So the first test we did was looking again at alpha regions. So we obtained the localized spectral admittance specifically for this region. And then we start running what we call geophysical inversion to estimate which set of parameters best fit this data. So that's what we did. So this is the observed admittance. This is our model. So this is where we stopped the observation because it is our resolution limit. And this is what we obtained in terms of parameters with Magellan data. So we have a crustal thickness that could be between 10 and 20 kilometers. The elastic thickness they vary from 16 to 28 kilometers. And the crustal density, again, we cannot constrain at this point. Then what we did was to try to make a gravity field that at a resolution that we expect for the Veritas team. So together with Gael and Elwan, and we looked into trying to generate some synthetic data. So what we did was to was to give to our gravity team some models with specific known crustal density. So we fixed the crustal thickness, the elastic thickness, and 3 different cases of crustal density. And then we give that, and then we added what we expect to be the Veritas noise to this data. And then we inputted this new synthetic data to the inversions to see if the inversion can retrieve well these parameters. And this is what we get if we fit each one of these curves. So as we can see, our inversion is working super well. We can constrain the crustal density with the crustal thickness and elastic thickness just with a few less than a kilometer uncertainty, and the crustal density super well as well, differentiating like a felsic to mafic compositions potentially. But we're giving a very easy job for the inversion, because the same model that used for the inversion is exactly the same as the one that we're giving as data, just adding some noise to it. So we want to know if we can do something more to make the data, maybe the synthetic data, a little bit more realistic and a bit more complicated for the inversion to retrieve back. And there's several ways we can do that. We can even discuss if you have your own ideas. But what we did for now is that since we actually know this part of the spectra from the Magellan data, we can actually use the part of the data that we know from Magellan and stitch this together with a logistic function, the synthetic data. So this is what we do. Again, now it's not as perfect, our inversions, but we're still getting very good estimates for crustal and elastic thickness, just a few kilometers uncertainty. And we can still differentiate between low density versus high density crust, which is very exciting. So, well, I have a lot of time. Just to summarize, with the current data gravity from Magellan, we cannot constrain the crustal density. We can constrain crustal thickness and elastic thickness with about 10, 15 kilometers uncertainty. And we are doing some inversions using Veritas simulated noise to see if we can retrieve these parameters better. And it seems like we can. We can retrieve very well these parameters. When we make the model a little bit more complicated, the fit is a little worse, but it's still doing quite a good job. And so basically the results we get is that with this data, we have uncertainty below 2 kilometers, plus or minus 2 kilometers for elastic thickness and crustal thickness. And we can differentiate between high and low density crust. So the main message that we're gonna wanna pass here is that geophysics can really help us, the other data sets, to really understanding the origin and evolution of these features and their composition. Thank you very much.
All right, thank you. Next up, we have Anna Gulscher speaking on diverse tectonic processes at Coronae on Venus, as revealed by joint analysis of modeled topography and gravity.
All right. Hi, everyone. I'm excited to talk to you today. And before I begin, I'd like to acknowledge my collaborators who are mentioned on this slide, but also just a thank you for the whole Veritas science team who all gave valuable input for this exciting work. So not a surprise to some of you, my talk will be about coronae on Venus. Coronae are these interesting circular-ish volcano tectonic features, highly abundant on the planet of Venus. They are defined by at least a partial ring of closely spaced fractures. And a recent database has detected over 740 of these features on Venus, which is actually really a lot more than has been previously cataloged. And here on the left-hand side, you'll see the spatial distribution of these. They occur in a large range of dimensions as well as morphologies, and are sometimes highly complex. And we also recently defined 11 of these subtle different topographic groups of these coronae, and that's just one example of how diverse these can be. And over the years, there's been many hypotheses of their formation, some of which are very different and many of which are only different by subtle foci. But basically, these formation scenarios can be grouped into two roughly different groups. They are hypothesized to form by lithospheric responses above either buoyant or transient mantle plumes and the related magmatism, tectonics, and melt pathways above these thermal anomalies, or on the other hand, by gravitational instabilities and downwellings. The data that we wanted to investigate for these features are both topography and gravity. So we have these amazing global maps of the Magellan mission, and they are plotted here, but they are both in highly different resolutions. So for let's go back, if I can. For topography, we're looking at a resolution of 10 to 20 kilometers, which is relatively fine compared to the features of our interest. On the other hand, gravity, here you have a global map of the Freer gravity anomaly. This has a typical degree strength of 60 to 90. And here on the left-hand side, you see the global distribution of this degree strength. And if we want to translate that in more sort of spatial terms, we define the spatial resolution as resolving a full wavelength. We get to values of about 200 to over 300 kilometers, with most of the planet being more on this coarser or larger spatial scale. So this is quite limiting in analysis that we want to take into account for studying coronae. So if we consider which corona we can even investigate in this coarse gravity field, we find that we define 76, so about 10% of all corona, to be resolved in the data set of the gravity field, which we define by having at least one wavelength resolved in a corona radius, so 2 wavelengths at least in its diameter. And the distribution is shown here. So for these corona, we only investigated topography and gravity data and tried to inform something about their present day state. So what we did is compare predicted topography and gravity anomalies from geodynamic models with the observations. What did we do? We chose earlier work from this 2020 work that defined 4 styles of different types of plume lithosphere interactions as responsible for at least a large part of the large corona formation on Venus. We extract the predicted surface topography and calculate the predicted surface gravity anomalies from the predicted 3D density fields of these models through time and to be compared with observations. And I want to highlight here once more that the spatial resolutions of the models and the observations are very different, especially in terms of gravity. So we do rescale the models into the Magellan gravity field resolution at each coronae to be able to compare them and see what we can and cannot detect with our current capabilities. So a very short recap of these scenarios. I'm not going to go into too much detail of them. I don't have the time. But here you see snapshots that show a top field of topography, a middle field of composition, and a bottom field of temperature. And roughly said, the 4 styles of geodynamic scenarios that we investigate can be divided into 2. We have 2 cases of some sort of plume-induced crustal recycling end member, where we have a quite buoyant plume and diapir that pierces through the lithosphere, pushes material outwards and downwards. And at the plume margin, you have either some sort of repeated lithospheric dripping and elimination events shown at the top, or for a stronger lithosphere, you have a short-lived radial retreating subduction zone, which is illustrated at the bottom of the graph. And the 2 other geodynamic cases that are also included in our analysis are more of the transient plume end member styles. We either have this scenario where the plume can rise a little bit and reach the bottom of the crust, and through that interacts with the surface through movements of material, tectonics, and melt emplacements. Or on the other hand, we have a plume that is completely basically stagnant underneath the lithosphere, stays there, and only through melt extraction has some volcanic and magmatic effects at the surface. So for these cases, here they are shown once more, we extract the topographic and gravity anomaly profiles. And these are shown here on the right because these models are very simplistic and radially symmetric. We look at profiles radially averaged over time. So for all these profiles, we compare these predicted profiles with the observations of the coronae. So let's take an example here. We look at the Yavin coronae here on the left, the SAR in the middle topography. And on the right-hand side, we plotted the Magellan free air gravity anomaly of this region. And in terms of topography, we handpicked two profiles. We do always systematically include the trenches if they are present at the coronae in these profiles. And we compare these with the predicted profiles from the geodynamic models that are rescaled to the observed feature size. So here you see such a comparison. In red, the observed profile, and in black, the best fitted model profile. And if we look at gravity, we do the same. We see in the black solid line the full gravity predictions of the geodynamic model. But in dashed black line, you see the downscaled model prediction in the Magellan resolution of this particular coronae. And that is then fitted to the observed profile, which is shown in red. So for this particular case, we find quantitatively by an analysis a best fit to a lithospheric dripping scenario in a very active and early stage. And more broadly speaking, this is consistent with various styles of crustal recycling scenarios at this particular coronae. Just a very quick other example, we here look at the Pavlova coronae, and we also match topography and the gravity here on the right. And we find for this particular case, the best fitting model to be a more transient plume and member style with the plume embedded underneath the crust rather than having these major tectonic recycling scenarios at the plume margin. So we did that for all of these 76 coronae on Venus. And roughly speaking, 52 of all of these corona bear gravity signatures locally that are suggestive of buoyant mantle material underneath. With our detailed analysis, we proposed the following classification across these coronae. In solid red fills, you'll see the coronae for which we find the best fit to either of the plume-induced crustal recycling scenarios. So plume-induced crustal delamination or subduction. And the same is for the solid blue cases, but we flag these differently because these coronae are embedded within rift zones, which is not something we particularly modeled. And then for the solid pink fills, those are the coronae for which we find the best fit for an active underplated mantle plume. So this is quite exciting, but these are sort of, we propose these to be geological active, and future work should really look at whether these have potential for present day volcanic outgassing, surface motion, and even seismology or seismic signatures. And obviously we're limited by various things, among which the Magellan resolution, as I already pointed out. We cannot distinguish subtle differences in the gravity anomalies, and there's a very high potential for smoothing of subtle but important anomalies. So very excitingly, we get new gravity data in the new missions. Here we see the Magellan degree strength field on the left and the predicted degree strength of the Veritas on the right. And I just want to highlight these extremely different resolutions of these fields. And also, just as a sort of forward prediction, using the same classification of how we consider a coronae to be resolved in gravity, the Veritas gravity field will resolve an astonishing 428 coronae, of which many of these coronae are also resolved with many more wavelength resolved than we can currently analyze. So this is very exciting, and I look forward to the science that this will bring. And that's it. Thank you.
All right, and if we can get the four speakers back up on stage for the Q&A. Please come up to the microphone with questions. And just a reminder to please state your name and affiliation when asking questions.
Richard Ernst, Carleton University, Ottawa, Canada. Matt, I just wanted to follow up on your presentation. That's a neat kind of modeling overview of the conditions and what, towards the changing the evolution of the atmosphere from habitable to non. And I just wanted to add in, there's another stochastic aspect that is potentially of significance. That is the role of mantle plumes and large igneous provinces. And, this echoes the paper I wrote with Mike Way a few years ago, where we were looking at sort of multiple random stochastic Siberian trap events leading to the runaway, with each of those producing 10 to 15 degree temperature increase, and superimposing those, three of those, you could get 45-degree. So, and I was noticing that the magnitude of one of those large igneous prominence plume generators, Siberian trap events, was equivalent to the kind of the notable 20-degree kind of shifts that you were noticing through, one was through the haze and stuff. I'm not sure how you would incorporate that in, but that is a way of potentially driving the whole thing, but also being a kind of superimposed 10 to 15-degree temperature increase. Any kind of thoughts on how that can be incorporated into the modeling in some way? No, the online people have to hear all the good stuff here.
You can use the podium mic if you need to.
There you go. Whoops.
So no, that's a really good observation and question. So for these models, I didn't get into detail, but they're the overturns themselves actually mimic like a LIPS generation event. These are large hemispheric scale. They're actually plume dominated overturns of the lithosphere. It's not subduction like we would see it on plate tectonics, but it is this massive plume induced melting event that occurs, massive decompression melt. So in the models, it doesn't have the specific mechanics and it doesn't have the pre-existing, say if there's a carbonate layer, for instance, that the lip would introduce itself into. It doesn't have that, but the volumes that we're talking about are hemispheric scale lip volumes. So it kind of is getting at that same idea. It's just doing it from the mantle side without dealing with the specific mechanics. But that can also be as you were saying, a superimposed signal on it. You know, if we put carbonate platform from an early habitable period,
Or even with not carbonate platform, the Siberian trap, you know, volume is
massive. Yeah.
I mean, there is what they call a thermogenic release of gas from interaction with units that you know, sills with units that bear carbonate. So that is a important part of it. Yeah.
Yes, absolutely. Yeah. So these are kind of in there, but there are ways to bring out more details.
It just doesn't require the hemispheric kind of changes. You know, the mantle overturn is not required then to produce it. So you can get, you know, a much more complicated kind of pattern of temperatures up and down.
Oh yeah. This would be completely superimposed. So I mean, this is a really good way to ratchet up those temperatures with both processes feeding off of each other.
Cool. Thanks.
Ian Flynn, University of Pittsburgh. This is for Anna. Great talk, awesome visuals. You got to at the end discussing your subset of corona you investigated and mentioned maybe geologically active. Have you looked to see any evidence of either recent volcanic deposits with them or high emissivity areas at that subset of corona you investigated?
So not thoroughly, is that how you say it? But yes, this is really on our minds and our thinking of trying to make this study relevant for people interested in targeting potential for the upcoming missions. I have like sort of my own notes because I have been looking at a lot of coronae for also side projects and the database. But that will be definitely our kind of next steps because not all coronae are necessarily associated with a lot of flows and volcanoes, but many of them are. So that is the next step basically. And I have some thoughts, but we'll look into it.
Thank you.
Francis Nimmo, UC Santa Cruz. This is a question for Julia. It was a very nice talk. I think your forward models assume that you have pure surface loading. If you put some subsurface loading in there, what would that do to you?
To me, nothing, but no.
To Venus.
No. Yeah, that's a very good question. So at this point, we only look at surface loading because from our previous studies overall, we found that the 2022 study we did, we saw that subsurface loading is not really probably not so important on plateaus. Like we don't see that we have an important contribution from subsurface loading, but I mean, it's not impossible to have that. Like in the inversions, like they could be there, they could also not be there. So because it was a small master project, we stick to the surface, but it's true that we can make this model with subsurface loading more realistic and do more complex tests. Yeah, for sure. Thanks.
Thank you.
Katie Broad, Baylor University. I have two questions if I'm allowed. The first one's for Matt. You mentioned that topography plays a significant role in your modeling. And I noticed you use present day Venus topography, but I believe the surface of Venus is like hundreds of millions of years old instead of, I think you said 2.5 billion years old is what you were modeling the atmosphere to. Is there a thought process behind that?
Right. So that particular, there was the aquaplanet, the bathtub ocean, and then 310 meters with current Venus topography. We use that because we don't know what the topography was in the past. So that's why we actually have that bracketed range. We could have an aquaplanet, potentially. I'm not necessarily certain that's accurate, but it's really to get a idea of how the climate responds if you have different topographies, because we can also put current Earth topography in there and play with it, which is a fun thing to do. But no, we're not saying that that was the topography 2.5 billion years ago.
Thank you. That makes sense. My next question's for Anna. So you mentioned you scale up your results from like 6 kilometers to at least a couple hundred kilometers. What factors did you take into account when you were doing that scaling?
Yeah, so we scale, up or down, depends on how you view it. But indeed, so basically what we do is, because we're in this spatial domain, we first get into the spectral domain, and then we really we identify the local degree strength at the corona of the gravity field, and we truncate the degree strength towards between kind of those degree strength, and then we translate it back to the spatial domain, if I have that correct, Gail.
Well, it wouldn't necessarily be like a one-to-one scaling kind of thing.
It is, but it is with in the spectral domain, because we have the gravity data in the spectral domain. For the rest, I think there are no other assumptions made. Yeah, that's how we do it. Thanks.
Adrian Broquette, question for Anna, DLR, sorry. Does your model predict time variable deformations of the surface that could potentially be measured by Veritas or Envision?
So yes, that's definitely from these 3D geodynamic models, you can extract a lot of different fields, out of which you have fields such as the snapshot of the surface strain rate, and stresses. So that is all predicted. But of course, if we think about fractures, then you actually get the opposite case, that our models are of poor quality relative to the observations, just by comparing the resolutions. Because for gravity, my models are great, a high resolution model, but for fracturing, my models or our general geodynamic models are often very low scale, especially in 3D. So we do want to think about this more and extract strain rates and think about that. But individual fractures in these large scale 3D models cannot be resolved. So for that, some other studies on 2D or some other studies are theoretically better, but we can still predict sort of the stress field of the area, out of which, and the strain rates, out of which I think you can still think a lot about the fracturing. So yes, this is extractable. And for now, we didn't include it because also STAR data is much more complex. You will have all the other tectonic histories at the surface there as well. But this is what we want to think about.
Okay, but I meant also like time variable topography and gravity, and if you would expect to see that let's say, the gravity field slightly increased between the Magellan era and the future Veritas mission. would that change be substantial enough to be measured for example, regions where you have active tectonics? And
I'm not sure if I got the question correctly with the gravity. Sorry.
regions where you have your active dynamics nowadays, you would expect to potentially see changes in topography and gravity. And my question is, could that be detected?
I think so, but this is really what we want to work on next. So I would say stay tuned. I think I have my thoughts, but I will also want to talk about this. I think there could be substantial differences in what we can see now and what we can predict.
Okay.
Absolutely.
We will ask one question from online and then come back to the room. So the question is from Mohamed Ben Marzouk, Carleton University, for the second speaker. So new detailed mapping of Abda region on Venus revealed that while different crustal blocks appear distinct based on surface roughness and continuous structural lineations can be mapped between them, this suggests a possible underlying structural connection despite their apparent differences. Could this imply that these blocks were once part of a larger unified crustal segment before later deformation? Any thoughts on this interpretation?
I think that's interesting. I think you're kind of saying maybe there was a block and then it became part of, like part of Abda was formed and then it was added on. Yeah, I think short answer is yes, I think that's possible.
Very nice set of talks here, so compliments to all the speakers. Question for Anna. With the corona, given the success in comparing gravity and topography for those large ones, does that give you the confidence to now go and look at the smaller corona and look at topography alone, or is topography alone too non-unique?
That's a good question. So do I have confidence of looking at the smaller corona? Not in terms of gravity for obvious reasons. I think topography, yes. Those 4 sets of models that we use in this particular study do predict very significant topographic variability across time and across scenarios. So if we account those for true, I think you can say a lot about topography, but I think there are a lot of caveats in still the models, as well as other formation scenarios that place different topographic sequences at different moments in time. So if I were to do that, I would want to, I think, consider a larger variety of geodynamic models. So I think that will actually make things less, not accurate, but less certain. So yeah, out of these models, they predict that, but I think there is a lot of other subtle difference models that should be taken into account if you want to look at topography only.
And a quick suggestion or a comment for Julia. Creating synthetic data that's as messy as the real world can be really difficult. But as has been pointed out in the previous talk and other talks, we have features on the Earth that may be analogs to the crustal plateaus, and perhaps try your model against the Tibetan plateau or a feature on the Earth that may have formed by a similar mechanism. Could be interesting.
Yeah, that's a good point. Thank you. Can look at that.
Question for Anna. With your modeling, right, a lot of it's focused on, okay, the annular structure that's quite visible and sort of modeling with respect to that. I wondered how the modeling would address the idea that for many of the corona, for a number of the corona, when we look more broadly, we see circumferential fractures that we think are probably underlain by dikes that may extend much further out and represent dikes being generated much further out from the underlying plume. We did that for Hengo in a paper by Tessier this last year that doubled the size, the diameter of Hengo from 1,000 to 2,000 kilometers. And so when you're doing a modeling over something like Hengo, can you rule out a plume head that's gone out 2,000 kilometers diameter, or 1,000 kilometers radius, versus one that's 500? Is that kind of ruled out? We also have a similar thing for Thermopolis. It was a Bethel et al. Paper, and we kind of doubled the size to about 900 kilometers from 500 kilometers diameter. So I'm just wondering whether the modeling will rule in or rule out the possibility of larger plume heads than we've probably considered for some of these things.
Yeah, that's a good question. And that's something I think is one of the things that could be really addressed by trying to tailor models to a specific region and then test different plume head sizes. I will say that part of the models that we have transient or underplated mantle plumes, and the stress field that they do create at the surface, even though the topography is quite limited to the area directly above the plume, the stress field is much more effective to a much wider dimension. I haven't necessarily quantified it because it was not the focus of the previous work, but this is something I think would be very relevant to try to figure out how the plume size, head size relates to the predicted fractures at the surface. So this is something that I think would be very relevant to look into. I think fractures can extend beyond the plume head, but I'm not entirely sure if you would really get sort of closely spaced fractures in that sense. So that is something I think the models do not address at the moment.
All right, thank you.
So question for Lauren. So you spoke about comparing Venus Highlands to regions in North Africa. What other places on Earth might you look for equivalent similarities? And if you wanted to look beyond just these sort of structural and morphological similarities, what additional data would you need?
So I think where I would look would be any really old continental area where we know from geological data and geochronology and paleomag that there has been a combination of crust in that area where we know there are suture zones and there are cratons coming together. So Northern Canada, and Paul has talked about this a lot before, but Northern Canada, Central North America, and definitely North Africa, Western Australia, anywhere on the continents that's really old and smashed up. And then I think ideally we would go to Venus and look at these things and connect and get some better geochemical and geochronologic data. That would be great. But other than structural mapping, I think that's our best bet right now, because I think that we can look at these suture zones on Earth and determine what's going on. And that's part of why I want to do field work, to go out and look and see what's going on at the field scale, and then try to compare that with what we're seeing in synthetic aperture radar imagery of Earth, and then to kind of quantify that and see if we can then apply that to Venus and the SAR that we have on Venus and compare that to our field results on Earth. So yeah.
All right, and let's thank our speakers one more time. All right, and just a reminder for anybody who might be joining us late, we're going into the last block of this session, so we will have 4 back-to-back talks followed by Q&A for all 4 speakers. So next up, leading off this block, the author listed was Erwan Mazarico, but we will have Gael filling in. And the title is The Veritas Gravity Science Investigation.
Thank you. So as many of you know, I'm not Erwan Mazarico, and today I will be giving this talk, giving a broad overview of the objectives, the products, and the science that we can do with the Veritas Gravity Science Investigation. As such, this talk was supposed to be given by the co-PI of the gravity investigation, Erwan Mazarico, but unfortunately, in light of a recent executive order, his travel was deemed non-essential and thus denied. So bad news, there are many bad news, but the bad news for you in this room is that now you're stuck with me. So you heard a lot about Veritas these days, and in particular yesterday from Suze Mercard, the PI of the mission, about the 3 instruments, 2 instruments and 1 investigation that we have on Veritas. And today we will talk about the gravity science investigation. Among the main science objectives of Veritas, many of these can be directly addressed by the gravity science investigation, and some of them can partially be addressed by the gravity science investigations. And these span from the deep interior to the surface, and so from the deep interior structure to the surface geophysics. The main scientific products that the gravity investigation will produce are the static gravity field and the tidal deformation, moment of inertia, and rotational state, so rotation and precession of Venus. And for those of you who like numbers, here I report the capability that we get from many simulations that we have run throughout the years. And even without going too much into details, the main take-home message here is that the static gravity fields, as you have heard before, will be resolved very well and very much better than Magellan, to better than 106 kilometers over 90% of the surface. We will measure the tidal deformation orders of magnitude better than Magellan. For the first time, we'll measure the tidal dissipation through the tidal phase lag. And the same goes for the moment of inertia and rotational state, and in particular precession, that will be measured orders of magnitude better than what we know right now. So any good gravity science investigation relies upon measuring very precisely the trajectory of the probe. This is enabled on Veritas by the use of the integrate deep space transponder to establish this coherent two-way Doppler link and radio link from the Earth to the spacecraft and back. This is produced by Thales Alenia Space and provided by the Italian Space Agency, and has strong heritage on Bepi Colombo and JUICE, in particular their Ka-band transponder. Veritas will be using two simultaneous frequency links in X and Ka-band, and remarkably, it will be the first mission to baseline Ka-band uplink on all DSN complexes. This allows us to establish this link that has a precision of 18 microns per second when we average over 10 seconds. This, keeping in mind that the way that we measure forces is by monitoring the position and the velocity of the probe, this should give you an idea of why we get such an amazing gravity field with Veritas. And also, we will not only use the tracking from Earth, but we will combine this with radar tie points. So basically, the radar on board on Veritas will image the same surface feature multiple times. And so using this in combination with the radio link to Earth, we'll be able to place very strong ties between the inertial position of the probe and the body fixed frame of Venus, so enabling a very precise determination of its rotation. So let's talk a little bit about what can we do with these measurements. One of the main open questions about Venus is the state of its core. Is it solid? Is it liquid? Is it solid and liquid at the same time? And from literature and from theory, we know that making some assumption, in particular assuming the composition of the mantle, the tidal love number K2 can help us distinguish these different states. Actually, Magellan measured K2, measured the tidal amplitude. But the uncertainty doesn't help us in distinguishing between the different states. While instead, this is, of course, the dark bar is the measured value and the rest is the uncertainty. While instead, if we look at the predicted values for Veritas, we see that the uncertainty that we will get will definitely help us in distinguishing between these different states. But I said before that we will not only measure the amplitude, we will also measure the dissipation, the phase lag. So this brings us another dimension in this phase space. So this is the same y-axis as before, but we've added an additional dimension on the x-axis. You can see that in this phase space, we can distinguish between different mantle viscosities, these different core radii, and somehow also in the colors, we can distinguish also slightly between different temperature profiles. What is still not very well distinguished is the mantle composition that is represented here by the different markers. And you can see here what is the predicted uncertainty of Veritas. So in this case, we will be able to locate very precisely a point in this plot. But okay, so how do we resolve this? How do we disentangle the composition of the mantle? Actually, I said before that we will measure also the moment of inertia, so bringing another dimension in this vision, in this phase space. So you can see there that this is the moment of inertia, and these are one of the main differences that we expect in Venus mantle is the content of iron oxide. So you can see that based on the moment of inertia, we can actually distinguish these two end-member cases, and this is, again, the predicted uncertainty that Veritas will bring. So, and that was all about zero-D modeling, so global properties of the planet, but we've heard, plenty of times today that we will get very good spatial resolution. What do we do with this? So again, going from the deep interior to the surface, here, the first thing that we can think about doing, and Ina Blesa talked extensively about this yesterday, I will just give a brief overview. At the low degrees of the gravity field, so when we're talking about the deep interior, we are sensitive to the mantle convection. So what the deep interior structures, the deep interior variations in density. why we can use this is to, among many other things, of course, is to try and understand what is the depth dependence of the viscosity. So what Veritas will bring is orders of magnitude better precision on the low degrees of the gravity field. So we will be able to characterize this much better. And okay, going a little more to the surface, we know that Venus has amazing geologic features that people have studied through time. So we're talking about coronae, tesserae, and so on and so forth. And these have been extensively studied through SAR imagery. These have been also like somewhat studied through topography, but not that much studied through gravity because of the coarse resolution. We have global results. So for example, the very famous map of the crustal thickness of Venus that has been derived with Magellan data. However, one of the questions we have is, are density variations related to similar to crustal thickness, or maybe not? They might be completely different. And the reason why we don't know that yet is for what Julia was saying. So we really need higher spherical harmonics degrees well resolved to actually produce a crustal density map. This is what we'll be able to do in the future. And to give you an idea, we've talked about this before, but I want to give a little more detail. So Anna showed these maps, and we see that, you know, this gives an idea of what's the spatial resolution, but maybe seeing this map on a presentation in 1 minute is not super explicit. So maybe what's more understandable is the ratio between those maps. So this is the improvement factor. How many times better than Magellan we're going to do in terms of lateral resolution of gravity. And so you can see that this plot spans from at least twice better to up to 5 times better in specific regions that were not very well imaged by Magellan. And if this still doesn't convince you that this is very good, another example. So let's say this is synthetic data. Let's say that a corona in the gravity field, this is the actual gravity field of a corona. So if we take this corona and rescale it to Magellan resolution, this is what it looks like. So not great, kind of a splotch of gravity. While instead, if we use the the Veritas resolution, this is what we see. So this is so much better for many reasons. First of all, the amplitude is much better preserved. It doesn't get smoothed out that much. We can better distinguish positive and negative values. We can better distinguish the contours of the corona. So this has, of course, strong implications in understanding and relating what we see. So the gravity data to geodynamical modeling and 3D modeling. So this is why, this is like the specific reason why in our previous talk, Anna was able to tell you that, you know, in Magellan, we were able to resolve with this methodology in the order of 50 to 70 coronae, while instead in the Veritas gravity field, we'll be able to resolve much more than that. So I hope that I've convinced you that we will get really interesting data, and we should be very excited about that. And since I have a little bit more time, something that I would like to discuss is that, you know, we will get additional data. So this is not in the requirements, but this is something that we can do anyway. So since we are using together Doppler links to Earth and radar tie points, we can actually monitor very well and very often the rotation rate of Venus. So we will be able to make very precise measurements every 2 days of the rotation rate of Venus. I don't have time to talk about why this is very important, but you can imagine that having basically continuous monitoring for 2.5 years, hopefully more, of how Venus is rotating will help us understand a little bit better the exchange of angular momentum between the atmosphere and the solid body. And since we are very sensitive to all these signals, we will be also sensitive to the thermal tides happening on Venus, and in particular on how these load the crust of the planet and how the planet responds to this loading. And in particular, this will give us additional insights on the viscosity structure. Not yet baseline, but possible, of course, atmospheric occultations, and still related to thermal tides, we will be able to actually provide multi-frequency measurements of the tidal response. But I'm happy to take questions about that, and you know, we can talk about it later if you want. Thank you very much.
All right, thank you. Our next speaker is Philippa Mason, speaking on surface change detection at Venus.
Thank you very much. Good morning, everybody. And I'd just like to present our thoughts on reliable change detection at Venus using analog studies. And I should thank my co-authors. This illustration is part of a review paper, which is being led by Justin Filiberto. But like Paul yesterday, I forgot to put the reference in, so I'm sorry about that. We have some challenges and some great potential for change detection at Venus. We have different types of change to detect, lots of different features, of course, but we have the issue of intermission change over a long period of time, the 40-year time gap, but also the possibility of repeat pass interferometry. And there are a mass of things that have to happen, and all the ducks have to be in alignment for that to happen. But there should be some places where that's possible, and that offers us another set of possibilities for change detection. So we have kind of non-coherent change detection using repeated images, and then coherent change detection using interferometry and some other things that come along with that. So we're all familiar with this now famous image of Mark Mons showing clear evidence of feature change and that occurred during the Magellan mission. But we're also aware of the great time and effort that went into finding that change. And so we have this long time gap, and we have a whole bunch of challenges, some of which Gerard referred to yesterday, different radar instruments and a whole bunch of system changes that we have to deal with across that time span. And then in the light of the wonderful new data we're going to get from Veritas and Envision, we have to get ready and prepare ourselves to develop some tools which will help us detect those changes. And we have a paucity of data. The images need to be precisely co-registered in order to detect the changes, and that demands topography. And the GDDR product is too coarse and too flawed to allow us to routinely do that with the Magellan data. So the terrain correction is crucial. So we also have unknown information, or let's say a great uncertainty about the types, scales, rates of changes that we should expect at Venus. So to achieve all those things and a reliable change detection, we basically need to really focus on Earth resources using Earth observation data, of which there is plenty, and to refine some techniques and support that with field work and laboratory analysis, etc., and simulation. So to illustrate one of the challenges, here are 6 amplitude images from Iceland at the Fagradalsfjall and Grindavik area, and these have been acquired by Sentinel-1. So we don't have to worry about those system changes. We have the same view geometry, but they're co-registered, they're terrain corrected, the same wavelength, etc. I would ask you, can you tell me where the new lava flows are in these images? And I might have a guess that there's some bright areas in the April 2021 image, but in actual fact, all of them contain new lava flows except for the March 2021 image. So amplitude changes can be really subtle and complex. And even when we have this beautiful data that are well suited for change detection, and they've been designed for that, it's not always easy. So we recently published a method, a kind of robust method to deal with non-coherent change detection from repeated images. So the issue is that if you consider Magellan and the imagery we expect to get from VISAR and VENSAR, they have this huge difference in spatial resolution. So to compare them, we basically have to kind of force one to match the other. But we find that if we take the Magellan image, or a small part of it, and we simulate what VISAR or VENSAR might see, we can see that the image histograms, even though these images involve a different number of looks, from different systems, the image histograms are fundamentally very similar, and we can model that and demonstrate that. If we compose a ratio of the two images and divide one by the other, we get this bottom image, which looks very noisy, because the common information between the two of them has been cancelled out, and we leave ourselves with the edge effects of the different spatial resolution and random noise. And the image histogram looks largely the same. But if we have a change between the two images, and here we have a simulation, we have a Magellan image and a simulation on the right-hand side where we've inserted some fake lava flows. What we end up with is a histogram which looks slightly different. It has two populations, the unchanged pixels and the changed pixels, which is probably a much smaller population. And that may appear to the right or to the left of the main histogram peak, depending on whether it's brighter or darker. And we can to split them and threshold those two populations automatically, if we wish, using something like the Otsu's method. And we end up with a kind of binary mask of changed pixels and unchanged pixels. And image ratio is a technique used widely for decades using Earth observation images to detect not only changes, but other things which are, maybe different for whatever reason. So that gives us quite a good way to detect changes in non-coherent imaging. So if we go back to Iceland, so here's an amplitude again of before a lava has been erupted. And here's a ratio of March 21 to November 2023. And here is the footprint of one of those eruptions very clearly in bright pixels. And you may not see that the histogram at the bottom has two slightly overlapping histograms. So we have the kind of noisy area, and you see that the topography has been cancelled out by this ratio operation. So it looks very grey and flat, and our changes are highlighted. And if I conduct the same thing with a slightly longer time period, we catch both of the eruption periods, and it's noisy and a bit messy. But again, the topography is kind of cancelled out. It's a very grainy image, and we have some bright values where we've got changes. And that includes lava flows, but also some building works that happened at Grindavik to try and deflect the lava flow. But we have a clear image that detects those changes. And we can use that to help constrain our rates and estimations of eruption rates. Now, what about repeat pass interferometry? Now, many of you are familiar, I should think, with the idea of differential interferometry. We see these wonderful fringes, these maps of deformation caused by earthquakes, but perhaps less familiar with its companion product, which is coherence. And coherence is a measure of the local spatial correlation in a window around each pixel, conjugated between the two SAR images. And the two SAR images must be coherent. There must be what we call a fringe pair with a suitable baseline. So it works like this, right? So we have three SAR images, time 0, time 1, and time 2. And we construct an interferogram and a coherence image between the T0 and T1. We end up, if you look at the second row, you see these little arrows which represent the scattering objects on the ground. And they've changed a little bit, and there's been an earthquake, so there's a shift. But the changes that have occurred in this case are half the radar wavelength. So the radar is very sensitive to things on the scale of the radar wavelength, so it's on a centimeter scale. And in this situation, we get a beautiful map of fringes of deformation, systematic deformation on the scale of the radar. If there are more changes than half a wavelength on the right-hand side, we lose the coherence completely. If the changes are greater than half the wavelength, we get nothing. But we can use that. We can use that information. So here is a coherence image of that lava flow at Fagradalsfjall, and here is the later lava flow. So coherence is 1 or bright if it's good coherence, and if the coherence is lost, it's 0. So the new lava flow has caused that loss of coherence. Very clear. Have another example. This is an analog I'd like to go to visit. This is Hawaii, and we have two amplitude images which form a fringe pair. I challenge you to find the lava flow. However, if we look at the coherence on the right-hand side of the bottom, it's really clear and very, very precise measure of, you count the pixels, work out the amount of material. And then to the left is the differential interferogram showing us the ground deformation, about 1 and a bit meters above, uplift and some subsidence. And this is a fissure eruption. So there's ground deformation we can measure, and there's random change that we can detect. And if you look at the map, the published map, they match very well. And here's a different example, right? So that was sudden coherence change. Now we have an illustration of gradual coherence change. We go to Chile. This is dry, super high. It's a volcanic landscape, volcanic and aeolian. Here's a Google Earth image. Here's a radar amplitude image. We have lava flows in the bottom right, and we have aeolian sand dunes, if you like, in the top left. Here's a coherence image after a month. Now after 2 months, after 6 months, and after a year. And what we see is the etching out of the beautiful festoon flows as the sediments start to move around, and we see dunes very clearly. There's no rainfall here. This is aeolian movement. And this is the only way we're going to detect dune movement, if it exists, sediment movement. So it's a really powerful technique. And we have a finite amount of change in a finite period of time, so we can constrain the changes we might see. So it'd be super wonderful if we can do any of these things at Mons and we pick out a lovely new lava flow. But how much change should we expect? We don't know. But we have lots of opportunities for change detection. I'm out of time. But we're continuing to work at various analog sites, and we're just beginning. So thanks very much.
Thank you. Our next speaker will be Joseph O'Rourke, speaking on true polar wander.
Hello, everyone. Thank you for coming. I'd like to begin this talk with a Jedi mind trick. We have observational evidence for true polar wander on Venus. All right. If that worked, you should be feeling a compulsion to define true polar wander. So if you don't know, true polar wander is the reorientation of a solid planetary body so that the axis with the maximum moment of inertia is on the equator. True polar wander is not a change in the spin axis of the body. It's not a change in the rotation rate of a body, and it's not a change in the atmospheric circulation with respect to the spin axis. So when we say we've detected true polar wander on Venus, what we're saying happened is that the spin axis stayed the same, the super rotation of the atmosphere stayed the same, but the surface features moved around. Okay, you might also want to review what a parabola is. The idea is that when an impactor hits the surface of Venus, it makes a crater, a plume of ejecta shoots out into space. The ejecta particles then sink back through the atmosphere at their terminal velocities. Because there's strong winds in the Venus atmosphere, those ejecta particles get blown. Because they get blown hundreds or thousands of kilometers. Because the winds on Venus blow mostly to the west, we get these mostly westward pointing radar deposits. They have parabolic shapes, so they're called parabolas. Here we added the red features, obviously, to the Magellan radar images. There's the impact crater, and you can see the radar dark pattern and then a radar bright interior to this particular parabola. Okay, so Trevor Austin did a ton of work on this. He resurveyed all the impact craters on Venus looking for parabolic features. He mapped them all. And importantly for this study, he put together a degradation sequence. So we think we can put the parabolas that exist into 3 different age buckets: young, intermediate, and old. And he also noted something that has only been glancingly referred to in the literature before. Which is that many of the oldest parabolas are not westward pointing. So earlier I showed you this young parabola. It's pointed almost perfectly west, but there's a lot of old parabolas that are misaligned with west, and they're often pointed tens of degrees north or south relative to west. So on average, these parabolas in the different age buckets have the same average orientation, but the scatter is much larger as you go to the intermediate and then the older age buckets. Okay, so this is a map of the global pattern of the global orientations of the parabolas. The lightest blue are the younger parabolas. You can see, again, they're mostly west. And then as you get darker blue, we go to the intermediate and older parabolas. And you can see that just visually, there's a lot more scatter in the orientation of the older parabolas. So at this point in Trevor's study, I was like, my God, this is true polar wander. Submit the paper. And if you don't believe it's true polar wander, just from this map, neither did our reviewers. Of course, the reviewers are all esteemed geniuses, some of whom are physically present in the audience today, so hello. And they very thoughtfully suggested that maybe we should like substantiate our conclusions or whatever. That was a helpful kick in the pants. We decided to embrace the challenge and step up our science game. And so we've done a lot more work in the last few months, and now I like double, triple super believe our true polar wander interpretation. Okay, in order to assess whether or not these orientations could be explained by the variability in the winds on Venus, we used the 3D wind profiles from the Venus Global Climate Database. This goes beyond like the Venus International Reference Atmosphere, bingo, and will give you a hint of what the 3D winds should be as a function of the time of day on Venus and the location. And with these winds, we can adapt a previously published model of parabola formation. The idea here is that you start with a sort of small circularly symmetric distribution of ejecta particles with a certain size dependence. So our models have like 1 million ejecta particles of different sizes. And then you model them settling through the atmosphere at their terminal velocities. And you calculate, based on their size, how far they get pushed, either west or north or south. And then what we get out of these models is a plot of the parabola deposit thickness as a function of location. If you just calculate the mass centroid of the parabola deposit and then look at where the crater is, you get an angle. That's the offset angle. All right, a point I'm going to make here is that missions like Venus Express and Akutski have not infrequently observed winds at the cloud tops that are pointed tens of degrees towards the poles. But these models reveal that most of the horizontal transport of the ejecta particles occurs deeper within the clouds or at subcloud altitudes. So even in cases where the cloud top winds are pointed like 30 degrees north or south, the overall offset of the parabola deposit from the zonal winds is smaller, usually much less than 10 degrees. Okay, so we ran these 3D parabola formation models at the locations of all the parabolas at all the local times, and these plots summarize the results. Oops, no, back. So spoiler. So here we have the sort of average offset as a function of latitude. The longitudinal dependence of the predicted offsets is like nothing. And the gold shows the from the minimum to the maximum predicted offset. And then this is just a spaghetti plot of all of the predicted offsets. Each trace is an individual parabola showing the variations with local times. Okay, so you can see that there's more scatters you get to higher latitudes, which you expect. But overall, the maximum predicted offsets, given the present day winds, are less than 10 degrees, which is exactly what we observe for the young parabolas. Okay, so now the question is, we can say, all right, the intermediate and the older parabolas, they're scattered in a way that's not explained by the variability of the present day winds. But what about the global pattern of their scattering? Like, do their scatters all agree with the planet, the solid body, having rotated together in a coherent way? And the answer is yes. So we performed a statistical retrieval of the most likely paleopole locations for the parabolas in the different age buckets. So obviously this has a limitation that we don't have continuous ages for all the parabolas. So you should think of these paleopole coordinates as sort of like average values, not necessarily precise locations. And surprise, surprise, these statistical retrievals told a pretty clear story. The paleopole of the younger parabolas is the present day spin pole, which is good. And then as we fit the paleopole locations for the intermediate and older parabolas, we get really nice paleopoles that are sort of marching southward in latitude along the same longitude line. Okay, and so these parabolic deposits are fairly ephemeral features, like the deposits are on average only like this thick or something. So they do erode pretty quickly relative to the age of Venus. We think the intermediate parabolas are around 10 million years old, and the older parabolas are maybe like 20 million years old. So if you divide 20 by 20, you get 1. And so we get an average true polar wander rate of about 1 degree per million years, which is basically the true polar wander rate on Earth. Okay, and interestingly, there's a really notable feature that is on the Great Circle along which we predict that this true polar wander has occurred, and that is the Beta Atla Themis region, or the BAT region. And so that's basically located on the equator of Venus today. And so a suggestion, and it's the area on Venus that we think is very geologically active today, could be generating these inertia anomalies that drive true polar wander. And so we're suggesting that the BAT region joins the pantheon of features in the solar system that are on the equator of their planetary body, either certainly or almost certainly because true polar wander has occurred. So this is not like, even if you haven't heard of it before, this isn't really an exotic process that we're only invoking for Venus. We're putting Venus into this comparative planetology context. Okay, so the big picture conclusion is that it is outrageously fun to use impactor-atmosphere interactions to constrain geodynamic processes on Venus. The specific conclusion is that older parabolas on Venus have more scattered orientations than younger parabolas. We think that's true polar wander. On Earth, you study true polar wander using paleomagnetism. We don't have that for Venus yet, so we have to use these impacts. But we think that true polar wander on Venus has occurred at about a rate of an Earth-like rate. And this is interesting because there's theory that suggests that true polar wander on Venus should be ludicrously fast because Venus rotates slowly with respect to Earth. but maybe this observation is telling us that true polar wander is governed by the rate of mantle convective processes that don't depend on planetary rotation rate as much. Okay, and Venus has been active, but we probably knew that already. Thank you all.
Okay, thank you. And our last speaker will be Stephen Kane on direct imaging of an exovenus.
Hello, everyone. Thank you for hanging in there. So I'm going to end this session with a look far into the future and at twins of our twin. And so I'm going to be talking about the prospects of direct imaging an exovenus. And I'm showing on this slide, for example, work I've been doing with Akatsuki data, where I convolved it to a much smaller set of pixels using a PSF noise model, which we might expect from a direct imaging mission. So before I get into the meat of this, then I want to go back to the decadals. Now, I do this a lot, and sometimes I ask you to guess which decadal this quote came from. I'm not going to do that this time. What I'm going to be doing here is that, of course, we've got the Astro 2020 decadal on the left, and we've got the Planetary Science decadal on the right, just merely to make the point that the top priority from the astrophysics decadal was under the heading of Great Observatories Mission and Technology Maturation Program. The survey's top priorities for this program is an infrared optical UV telescope optimized for observing habitable exoplanets and general astrophysics. And of course, there are numerous references to the top priority regarding Venus, which is ascertaining the past history of volatiles and the potential for surface liquid water. And my conclusion from this is that when we put these two together, then the overall cross-disciplinary motivation from these two decadal surveys is a new mission, which is, of course, called the Mean Lean Venus Finding Machine, the MLVM. Sadly, the astrophysics community decided not to go with that and went with Habitable Worlds Observatory instead. But don't worry, it's going to work for us. This is a very broad mission. There's a lot of science goals that are going to come out of HWO. Now, for those of you who may be unfamiliar, this is somewhat a 6 to 8 meter class of telescope that is being proposed. As you can see there in the top right, the top level requirements is that it be able to search 100 nearby star systems to find around 25 potentially Earth-like worlds around other stars. And so what's shown here is an example which was produced by several folks who have been able to create simulated data for HWO. And the main point there is that this is the solar system at 10 parsecs. And the inner working angle does allow for the detection of a true Venus analog. But there are many other Venus analogs to choose from. You've heard me talk about this before in the context of how many exovenuses have we found? Well, it's been more than 10 years since I created the Venus zone concept. And at that point, there was only tens, but now there's hundreds. And that's rapidly increasing. The Transient Exoplanet Survey satellite, TESS, is approaching its 70th anniversary since it launched, and it's still going strong. There are many more exovenus candidates that are being detected, and there are many, many more to come with future missions planned. And so this is a plot that was produced by Colby Osberg. He has he's in the audience. He's giving a talk this afternoon, and he has been working very hard on constructing a list of the potential Venus exovenus candidates. But and we're going to need a lot more of these, particularly when it comes to the constraints of having these be the nearest stars. These are transient planets. I'll come back to the consequences of that in a moment. So for the Habitable Worlds Observatory, I'm leading a science case for discovering and characterizing exovenuses. And There are many of these being put together. You may have seen the huge amount of activity surrounding HWO and the way it's really grabbed hold of certainly the astrophysics community, but there are a bunch of different subgroups, some of which are solar system focused and certainly exoplanet demographics focused. And so this falls within both of those contexts. So I've put a QR code there because this is really a community-driven effort. If you are interested in being involved, you are more than welcome. That QR code will lead you to the document where I am constructing this science case. And if you have comments, feedback, then I would love to hear about that and have your comments. You can comment directly on the document there. But essentially what we're going to be doing is taking a lot of these exovenus candidates, which Colby and I have been working on for a long time. We're going to be placing that within the context of the inner working angle of direct imaging mission, which is, of course, one of the main constraints when you're trying to look at planets which are relatively close to their stars. How many of them will actually be able to be observed with a mission like this? And actually, there's quite a lot. There's quite a lot where we can do this, but also, and as many of you have heard me say before, characterizing Venus and truly realizing what has been outlined within the Planetary Science Decadal is a two-pronged approach. One, of course, which is the intrinsic analysis of Venus itself, but the other is placing it within the broader context of the broader exovenus population, and whether any of those are in transitory states of their evolution. And so even those planets which are further out at the outer edge of the Venus zone or even in the habitable zone could be in post-runaway greenhouse states. And that would be very, very interesting to discover. Now, one of the things I'm saying down here at the bottom is that there's essentially two populations, one of which is transient planets. Those are difficult because transient planets tend to be close to the star around very faint stars, and that's because of the observational bias of that technique. I expect that the more viable candidates will actually be non-transient planets around brighter stars, but then you run into degeneracy issues where if you don't know the radius of the planet, if you're trying to constrain something like the albedo. So something to think about. But the reason why we want to go down this particular rabbit hole when it comes to Outer Worlds Observatory is because we live in the area of JWST, and JWST is mostly observing in the infrared, and there's some really nice absorption features for things like CO2 there, but there's degeneracy there. And in order to break that degeneracy, we need to go to other wavelengths. And an example of this, here are some more plots, which were once again, these were produced by Colby Osberg. And this is showing near infrared for a true Venus analog. But in this case, we'll put it at 1 AU, and you can see how the sulfuric acid haze really conceals a lot of the interesting features we might be interested in, such as sulfur dioxide. But if we go into the ultraviolet, then some of these features start to pop out, such as the sulfur dioxide. And so we can break a lot more of the degeneracy by going into the ultraviolet for these kinds of candidates. Now, I want to speak through a little more of the broader, like longer term and pathway forward on this kind of a topic. First of all, like I've said, well, one thing we certainly know from the Kepler mission and other missions that have come after, fortunately, we've got a lot of candidates to choose from. So that's great. And as well as TESS, we've got Plato, we live in the era of extreme precision radial velocities. And so we're going to have a lot more candidates coming down the pipe. And Colby will be giving a talk in the session this afternoon about exoplanets. And secondly, although I mentioned that the sulfuric acid haze certainly is a problem in the way it truncates spectral features for a true Venus analog, that may not always be the case because that's sensitive to the pressure temperature profile of the atmosphere of the planet that you're interested in. And some of the work that that my student Emma Miles has been doing, and who is also giving a talk this afternoon, is looking at what is a far more common case, which is super Venuses, where you have a much thicker atmosphere, very different pressure temperature profile. And in some of those cases, the sulfuric acid haze goes away, even though it's in this post-runaway greenhouse state. So don't always assume that you're going to have that issue. And that's going to be really interesting going forward. So in terms of looking forward, as I mentioned, we're in the era of JWST. Many of you may have seen that the Cycle 4 selections have come out, and there's some really nice stuff in there. There's a lot more terrestrial planet atmospheric characterization coming our way, particularly at the inner edge of the habitable zone, the Venus zone, where we're concerned with things like atmospheric erosion. But of course, this is where the missions come in, because they are going to be deployed right in the middle of the JWST nominal lifetime. And so that's going to be important, not only informing those, but of course, what's coming at the end, which is Habitable Worlds Observatory, the LIFE mission as well. So I'm very excited of putting all these pieces together for the community. Like I said, community effort. So love to hear your feedback. Thanks, everyone.
All right, thank you. And if we could have the last 4 speakers up on stage for Q&A, please.
Peter James, Baylor University. I am not one of the esteemed scientists piling on True Polar Wander, but I'm happy to jump on that bandwagon. No, I like it a lot. So on a lot of planets, you have impacts that cause True Polar Wander, and I assume you roll that out. The idea of plume volcanism has a comparison to the moon, where that's the upwelling under the PKT is thought to have driven True Polar Wander. On Earth, there is also this the effects of there's a Chandler wobble, where you have atmospheric pressure variations that that affect the spin. And yeah, I wonder. And the other thing about the upwelling idea is that 20 million years is a pretty short timescale on convection timescales, and so is that something that you see operating on those timescales?
Yes, sir. All good points. To your last question, I think the idea is that the mantle convection could have been happening on slower timescales, and we're just sort of seeing Venus respond on the appropriate timescale. So yeah, if the plume has been, just say, rising under the Bat region or something, then we're seeing just the response over the last 20 million years, even though that process has been slower.
Ralph Lorenz, APL. Question for Philippa back there. You made a great case for under ideal circumstances, interferometry as giving a literally black and white indication of a surface change, a new lava flow, and whereas the backscatter based examples you showed from the Earth were kind of gray, and those were under the same incidence angle geometry, and it gets even more fuzzy if you have less ideal comparisons. Is there anything in the rheology of Venus lavas that might lead you to expect, for a given volume eruption rate, cubic kilometers per year, that you generate more area times contrast in elevation terms, that you might have wider, thinner flows that give a stronger signal in topography versus backscatter? And also, sorry to convolute the question, the fact that interferometry looks really good per observation may still mean you have more opportunities to see larger area time products of change detection opportunities with backscatter, because you don't need necessarily the exact same geometry. So is there a sort of strategic sense of what's going to give the best payoff for example, ENVISION specifically?
No,
Yes, good question. I don't know. I think the answer is probably yes. I think we have options for, you know, the different situations, and I think we take whatever chances we get. The sizes and scales of the features, how much change might we expect in the last 40 years versus when we catch them? How fresh are they? How different is that? How differently are they? How different are they radiometrically? These are all unknowns and things that we have to try and model and, you know, and simulate, if you like, and test using as much different radar as we can get our hands on over different types of terrain. But yeah, I think we, you know, it's the easy win is the non-coherent change. As long as we can repeat image, we can maybe catch something which is different. But how different they need to be is another question. Then different from their background, yeah. But the thing is about ratio. You know, if you divide two images by each other, you cancel out everything that's common. But if the thing that you're trying to look for isn't there, you're going to highlight something. So we have to be skeptical about what comes back. But, you know, it will detect some, if there's any change at all. Of course, we don't have to worry about vegetation and the people and buildings. But if there is any change, it warrants investigation. And we can use a very quick tool at very low resolution to kind of trigger something's changed. It needs to be investigated in more detail. And I think that's the approach probably that's necessary.
Jim Cutts, JPL, a question for Joe Rook again on True Polar Wonder. Actually, two questions. So first off, you know, we have Envision and Veritas coming along. Would you be able to get a better definition of these features from that mission? Second question, you had a throwaway line about magnetic detection. Surely that would represent a very different timescale for Polar Wonder, and how different would the measurements there, and would they be complicated things by things that might be structural in nature, incipient continental drift?
Yeah, I think we would have to be ridiculously lucky if we found any evidence that Venus had a magnetic field, a global magnetic field, like 20 million years ago. That's basically the same as today in geologic time. So I kind of doubt we have such young magnetism. To your first point, yes, Veritas and Envision will help tremendously with this sort of study. James Keene, a couple of years ago, led a study with his co-authors and did sort of hypothetical wandering paths for Venus based on geoid anomalies today. The problem there is we don't maybe understand the geoid anomalies as well as we should because of a limited resolution of the gravity data. We also don't have any idea of their relative ages. So Veritas and Envision will give us relative ages of these different features and tell us where the inertia anomalies are at present day. And that will help put together these sort of hypothetical reconstructions.
Hey. Anton Ermakov, Stanford. Also a question for Joe. Hey, great talk. So very interesting. So I guess I have also sort of like two questions. So first is kind of like maybe a shorter one. So when you do the atmospheric modeling for different position of the pole, what do you need to take into account this in the atmospheric model? And if yes, does it have any effect?
Yeah, so I don't think it has a huge effect. And the reason is that I alluded to this, the longitudinal, like the actual probable location only matters in terms of the latitude. Like the longitudinal variations, which are mostly caused by the effects of the surface topography on the atmospheric winds, they don't seem to be that large. And the latitude changes we're predicting are only like 10 or 20 degrees. So that means that if the atmospheric circulation was the same 20 million years ago as it is today, just the fact that you're moving the latitude of the parabolas wouldn't change the expected orientation that much.
Okay, and second question is, I wonder if you get like a constraint on the like elastic thickness, you know, like heat flux, you know, thermal state of Venus from your like 1 degree per mega year.
Yeah, I'm unwilling to offer a precise statement about that, but in theory, I think you could, because there's a lot of much more sophisticated geodynamic modeling you could do to predict the rate of true polar wonder. So, yeah.
Thank you.
Yes.
Adrian Broquet, DLR. I have a question for Gael. So there is recent work that suggests that on Mars, we might be seeing some long wavelengths changes in the static gravity field that could potentially be linked to mantle convection. Is there hope to see changes in the static Magellan gravity field at the long wavelength as compared to what will be measured by Veritas?
Okay, that's a good question. And yes, there are different ways in which we can look at that. So the first one would be to just compare the field that we measure in 2031, 32 with Veritas to the Magellan one. At that point, we need to discuss what is the sensitivity you need there on the low degree coefficients, because the Magellan sensitivity on the low degree coefficients, although good, is not 10 to the minus 12. So that's something we can look at. But something else we can look at, and I mentioned it in my talk, is that we'll be able to measure thermal tides, and that is measured through periodic variations of the low degree gravity field coefficient. So we do have sensitivity on that. At that point, the big question is, can we disentangle the effect of the geophysical effects from the atmospheric effect? And that would be somehow model-based, but there might be, I would say, good argumentations to say that we have like very, very different frequencies, so we can try and estimate very different frequencies that should not mix with each other. So that's definitely something let's keep talking about this, because that's something we can look at.
Okay, thank you.
Hi, Marshall Eubanks from Space Initiatives. So this is for the second speaker recently. A few years ago, JPL did a study where they concluded that you could actually have retroreflectors on the surface of Venus that a orbiting radar would see, and that would be fairly low mass and fairly low impact because they're just basically sheets of metal. Would that help in your registration of these radar images?
Yeah, I think that there would. We've had lots of conversations about this sort of thing. Wouldn't it be lovely if we could do that? Yeah, that just little internal GPS points. They would of course help. So can we do that? That'd be good.
Well, you won't do it for my money, but and actually on that point, the 1 degree per million years is 10 centimeters per year, and you might actually be able to see that geodetically if you had reference points like that on
Indeed.
the surface. Thank you.
No argument from me.
Lynn Carter, University of Arizona. For Joe, that's really cool. And I was just wondering if there's other surface features that could record the polar wander, like, I don't know, Yardangs, or is it just too much of a mess with like local winds or?
I think the Yardings would probably be, because the parabolas are nice because they rely on the mid-altitude winds, which you can, which maybe don't change as much as you rotate the surface. So yeah, I'd love to think more about trying to use other sedimentary features, but as you say, it's not so neat as to assume, oh yeah, the surface winds are all exactly westward pointing, so harder to do that.
Ian Flynn, University of Pittsburgh, for Philippa. Interesting talk. Great to highlight some of the limitations of ADAR. At the end, you brought up the point of applying this to sedimentary process, the dune migrations. Have you considered applying this technique to pyroclastic flows or something to see what amount spatial coverage and thickness you would need if we were to apply the same technique to Venus at some of the potential pyroclastic flow deposits?
I haven't done anything about it, but I've certainly thought about it. But yeah, I think that's something to look into. But yeah, as I say, we're just sort of beginning to try this out, and that's a great idea. Thanks.
Yeah. Thank you. Great talk.
Adrian Brockett, DLR again. I have a question for the third speaker. So true polar wander can lead to pretty substantial stresses on the crust, right? Have you looked at the predicted stress pattern that you would predict? And could you look at if you have, for example, faults that align with your predicted stress field? Because this would potentially be a good region to look at for seismic activity, for example, on Venus.
Yeah, that's a great question, and we should look into it more thoroughly. But because Venus's rotational bulge is so small compared to Earth, like the strain you need to accommodate to have true polar wander happen is like really small. So I think relative to Earth or Mars, the stresses or the strains associated with this are going to be a lot smaller. But that's just my hunch. I haven't done all the thorough math behind that.
Okay, thanks.
I have like Ralph Lorenz APL. I have an esteemed pants kicker question for Joseph. You indicated you segregated the population into 3 epochs, you know, the old, intermediate, and young, and there was 20 million years.
Roughly, yes.
Yeah. So if memory serves, a few tens of millions of years was the timescale that Bullock and Grinspoon proposed potential climate change on Venus from volcanic injection changing the greenhouse effect, and that would presumably manifest also in a change in circulation. So could that be an explanation instead?
It very well could be, because we can't sort of independently constrain the atmospheric circulation. But the fact that the older parabolas and the intermediate parabolas are still on average pointing west, I don't know, kind of tells me that like on average, the circulation was pretty similar than it was today. Certainly there was still super rotation in general.
Yeah,
so I guess the question is, like, would these climate changes have made the meridional winds faster, right? Like, is there a stronger Hadley the Hadley circulation
So
actually doesn't
somebody
really-
with a GCM needs to explore that.
Yes, GCM people, please help.
Joe, sorry, no, one more.
I love it.
Yeah, I'm sure you do. That's great. What about oblique impacts, right? Because it's that going to sort of spray the dust in a particular direction. And so can you mitigate that in terms of your interpretation? Do the parabolas truly reflect, regardless of impact, you know, how oblique the impact is, the true wind direction?
Yeah, the force revealed to me that this question would be asked. I expected you to wear like a different costume, but yes. So yeah, probably the impactor angle might induce some asymmetry in the ejecta plume, which would lead to an asymmetry in the parabola. But what I would say is that there's not a bias to the direction that the impacts would hit for these parabolas. So in general, this would just sort of add scatter.
Well, it could be, but like there's this recent paper that talks about a whole series of impacts on Earth in the Ordovician. There's a sort of a notion that there was even a sort of a ring around Earth at a certain point. It's a new publication, so there's a whole series of impacts at a particular time. You know, I'm not sure what the orientation would be. Or we had a story with respect to a series of splotches that was very oblique, the splotch chain that was one of our group published a few years ago,
Yes.
right? Very oblique. And so there were a whole series of impacts. They were splotches, so they weren't craters per se, but there were a series of bodies coming in, like on Jupiter or something, coming in at some angle. So it's sort of a statistics things. How many of these things do you have in your old record? How many items are there that would have to be, you know, part of a series of things coming in one angle?
Yeah, so I mean, I haven't investigated specific scenarios, but I'd say the old parabolas are distributed all around the globe. And so it's not like there's just a chain
And it's
of
a
old
large
parabolas.
number of them. How many are in the old category?
Oh, like 20 or so. Yeah, so it's not a huge number, but the thing is, I mean, and this is why the fact that our statistical retrieval like kind of worked gives me confidence, because you would have to bias like the ones in the northern hemisphere towards the north, and then the ones in the southern hemisphere like towards the south, in a way that could be replicated by just rotating the whole globe. I don't know, it seems pretty hard to get that sort of pattern just with a few stochastic impact chains, but
yeah. Okay, well, it's certainly very intriguing. And
thanks. Yeah.
good.
So Marshall Eubanks again, this is a Veritas question. You are, thank you. It's like denial of service there. I can't see it anybody. You were proposing that you could look for the atmospheric barotropic thermal tides through their gravity effect in 4 days or something like that. And I remember Bruce Bills, you know, it seemed to feel like that could definitely be seen in gravity if you had a good enough gravity field sensor. And if you had a probe on the surface for a little part of that time with a barometer, which they should have, that measured the gravity tide at that location, what would that help like break the sort of the coupling with the geodynamics that you're worried about?
Definitely. There are a bunch of couplings that we, need to care about. And indeed, we resolve them mainly, not mainly, no, but informed by modeling, by GCM modeling, because we know what's the expected main the Fourier spectrum, basically, of the thermal tide from GCM modeling. So we can use that to inform our recovery. if we had a measurement on the ground, it would be amazing because we could completely disentangle that from the measurement of the body tide at that point. Because, you know, the body tide and the thermal tide are just both tides. So periodic terms in the J2, C22.
What you're saying is body tide is really the load response, but the ground is deforming because it's got the gravity.
Yes,
the
yeah, but also
thermal
what I'm
tide
saying
on
is that if we actually measure the pressure variations at the surface, at that point, the thermal tide is fully understood, the atmospheric thermal tide is fully understood, and we can completely disentangle that from
So
the
you
solid
wouldn't
body
need
tide.
Too much of that. It's not like you'd need a year-long mission or anything. A few days would probably be enough for that.
Well, actually, the period of the tide is one alpha Venus day. So I would measure, you know, for probably at least
120 days or something more like.
Earth day, 116 days, yes.
All right, thank
Earth
you.
days, yes.
Hi, I have a very naive question for Steve Kane about EXO. Well, I don't, you know, I'm a geoscientist. So my question is the definition of an exovenus purely based on this, on the atmosphere and the spectra, is also the size and mass? And then what would be the difference between like an exovenus versus an exomars, for example, that have kind of CO2 atmospheres? Does that make sense?
Yeah, no, that's a really good question because, you know, we have a tendency towards taxonomy, which I always try and resist with every fiber of my being, because I think these planets exist within continuums, not only in their current state, but their evolutionary history. And so when it comes to an exovenus, the way in which we define it, say in the diagram that I showed that Colby produced, that is including all planets that have a known radius that is less than 1.5 Earth radii, and fall within this region determined from one-dimensional climate models where they might be pushed into a post-runaway greenhouse state. But if you consider that, for example, Venus, if it had a temperate period, or insofar as Earth might have a future post-runaway greenhouse state, then is Earth an exovenus? You know, like that's the sort of thing that you run into. Now, when it comes to something like an ExoMars, you're really starting to run into issues regarding atmospheric loss. So depending on where it is with regards to what those limits are, and that's something that I wasn't able to mention, that the Venus zone is undergoing radical revisions at the moment, that we're recalculating what that inner edge looks like. And that's based on JWST data, which indicates that atmospheric erosion may be far more serious than we originally thought, and that many planets, regardless of their degassing history, may not have the opportunity to transition into a post-runaway greenhouse state. So that's a very convoluted answer to your question, but it's based on this multi-dimensional aspect to it, most particularly the axis of time, because not all planetary systems that we look at will be 4.5 billion years old. Some of them, like the TRAPPIST system, will be 8 billion years old. Some will be 2 billion years old. And so it's really looking at their current state and learning what those evolutionary tracks look like.
Thank you. And so just a quick reminder, if you have not had enough Venus yet already, there is a virtual poster session this evening. And don't forget that at noon in Creekside, we have the Venus Community Interest Meeting. And so with that, let's thank all of our speakers one more time. And the techs also.
And there's some candy, I think, left if you want some candy.
Thank you very much for coming.